population. Sorry. Say that. So we can tell you a little bit about the nature of the student population, but we also can really highlight the growth that's occurred over the last 10 years. We've entered the interesting phase in with regard to academic institutions. Some, especially the smaller students, have shrunk or are facing pressures relative to enrollment. Ours pressures are much different. If anything, we are growing faster than our. We struggle to keep our facilities growing to be able to accommodate the educational mission as well as the research mission that the faculty we bring in to be able to support the student educational experience. So we're up now at over 31,000 students, approximately, I would say, where are we at now? About 25% are graduate students. And actually, it's fallen percentage-wise. As we remember, our origin was the Graduate Research Center in the Southwest. So we and very much were oriented towards graduate students early on. And now we're becoming probably a little more familiar to the idea of the conventional public institutions that you see across the country. So next slide, please. I'm going to tell you a little bit about these students. Vast majority from Texas. Good number of freshmen, increasing numbers of freshmen. And probably the most interesting thing, it's most indicative of the quality of students that we have, is the large number of freshman National Merit Scholars. May seem kind of insider baseball term, I was going to say it's a big number. This puts us in the top 5 of public institutions, not in Texas, in the country. And we did it by putting a lot of money into National Merit Scholars. Oh, they get paid to come. So this is an engineered, this institution's been engineered and designed to have an excellent student body. And we got there and have done it through the insight of leaders past and part of the history of UTIs. So next slide, please. So what kind of degree programs do these kids go into? We're largely a STEM institution. Again, we don't have a football team. We have chess. We recruit chess players, and we have very good chess. Thanks to for other places. We also have senior design teams, engineering that win national and have a streak of winning the national competitions, ASME for some spring of number of years. Why? We had that, but we made a lot of investment. Or made a lot of investment in capstone programs for senior design. We hired a bunch of TI engineers, retired engineers to run. Did great, and it succeeded beyond all dreams and expectations. That's majority of students go into STEM areas and say STEM the expert down because management or school management is really quite exceptional. And that's really start to shape who we are. Again, our DNA institutionally is intimately tied with the founders of TI. We have a really, we have a tremendous amount of appreciation and really the intersection of management, which becomes innovation and entrepreneurship, woven in with STEM areas, really defines who we are. Next slide, please. Okay, a little bit by numbers. We still are a relatively small institution in terms of tenure track back. We're growing this. And it's no doubt it will be up to 700 over the next several years. With it, I think that the probably most exciting numbers to identify in all of this is that are some of the numbers that we have in our own venture development. And that venture development center comes from the largest in our region for supporting small businesses. And we haven't stopped in terms of what we're doing in venture development. Get the next slide. And we've really formed and have had a really nice relationship with the city of Richardson. Richardson, Texas was the home, of really the telecom industry. And with it, we're working with the city of Richardson, the Phoenix rising from the ashes of what was the telecom industry, to establish a university presence to be able to thrive and develop advanced manufacturing and other kinds of domain areas. And with it, we've actually established a development oriented outpost. It's only 10 minutes from campus, where we have various centers that are oriented mainly by areas, by which I mean artificial intelligence. We have something mostly working in drones, integrated data fusion for drones. and as well as a Center for Smart Mobility is actually working closely with the city. How many of you have been stopped at a intersection at 2 a.m. in the morning with a red light and wondered why there's nobody coming? And well, that's what Cosmo is working. They're trying to create a smarter traffic grid and working closely with the city. I think about how do we handle timing at stoplights in ways that make sense to increase mobility and actually reduce some of the carbon load that happens by stopping and starting. Okay. So I think one more slide, I think we're going to show you where the location is. Again, this bothers my sensibilities. I like north being north. This is north. But our campus being very, very close to this Richardson IQ area. The campus itself, I think we're 400 plus acres of land. We're the Richardson IQ is one that we're excited by because it's basically 1,200 acres of typical Texas tech park kinds of areas, and where it becomes a bit of a blank slate for us to work with the city and help revitalize and bring some economy, or at least technology economy, job development, workforce development opportunity. So with that, I'm very happy to turn over to our next speaker. And we're going to start hearing more from our friends in the UAE. Okay, so thank you very much. And again, I hope you'll join us afterwards. Networking, the true inspiration for a collider is networking. And I think that we look forward to having further discussions to see how we might look at that. Thank you. Yes, sir.
Right, can everyone hear me? Am I loud enough? It's funny you mentioned North Texas. My first experience in semiconductors was a visit during I don't know if you remember if they still have them. There were summer experiences for undergraduates, they called REUs. Right, so was at University of Arkansas. We went to Texas Instruments to see Tchaikovsky build. I remember the first time I saw like a 5 foot tall crystal, and they had these giant concrete cylinders. They had a pole, and you go peek over the edge of what's happening over. So it's a small world, I guess, right? Back in contact. So, good morning. My name is Benjamin Newton. As I said on the slide before, I am a product lead for wide bandgap semiconductor with the manufacturing and industrial technologies division. I will be presenting to you the network C3 wide bandgap semiconductor, at least part of its portfolio. C3 being command control communication for those who we have quite a few acronyms. If you already know them, I apologize, but tend to err on the side of caution when dealing with people outside of the workplace. Now, please do it. I don't know how many of you are familiar with the different types of jobs we have at AFRL, so I'll do a little bit of explanation at the beginning. I am like I said before, I'm a product lead, and that means that I am in charge of a portfolio of technologies in my division, in my area at AFRL. Those have to be wide bandgap semiconductors. Now, as a project engineer, I'm not doing pure research on my own. But we do have pure research people who I am in constant contact with, asking questions. They're much smarter than me. I pick the brains of strategy, where to go forward in different areas and the like. Now, being a project engineer, I will have some more explanations as we go along through my talk. What that means. If I were to use 2 words to describe AFRL, I would use technological capability. What I mean is that we provide technological capability. It's almost, I want to say turnkey almost, because what comes from on high is they tell us that there's a need, there's a gap, there's something we need a capability for. And we utilize all 3 of these sections in order to fill that gap. And it takes all 3 of those sections. We have the pure research people, they're looking at the latest, greatest thing. We have people like me that are minus 2. We provide the Air Force with technological capability through a manufacturing lens. And that'll make more sense as I move on. So we keep track of the science and technology and apply manufacturing knowledge and capability to improve or revolutionize warfighter capability. Next slide. We are located in building 654 Wright-Patterson Air Force Base in Dayton, Ohio. The Network C3 product area is within the Functional Systems branch, which is part of the Manufacturing Industrial Technologies Division, which is part of the Materials and Manufacturing Directorate, which I have highlighted. Right, you might not remember all those. Some people know us as Mantech, but if you know us, we are the Manufacturing Industrial Technologies Division, because we have an Industrial Technologies part, which will also explain. Other people that will be coming to speak after me will be part of, some of them might be part of RX, but some of them will be part of other different divisions that work on this. They might even have the same slide. Next slide. AFRL has investments in all four of these sections in the Manufacturing Industrial Technologies Division. We collaborate and track innovations in all of these sections, which the bulk of the programs that we initiate and manage, they lie in 6-3 advanced technical. That's usually where my baby begins, right? Next slide. So, as mentioned earlier, we look at technological innovations through a manufacturing lens. We track new developments and techniques in manufacturing. Many times, funding and developing many of these new techniques, or bare minimum, helping to buy down risk for the adoption of new techniques by the industrialists. We work to reduce cost and cycle time and maintenance, repair, and overhaul. That's what the MRO stands for. We also provide subject matter expertise in manufacturing, and we do manufacturing readiness assessments. Right. We are also the Manufacturing Industrial Technology Division, also the executive agent for the Defense Production Act. And Title III, we execute all products in the Title III portfolio. I don't know if you've ever heard of the Title III. It became, I guess, more known during COVID. They were trying to ramp up production of certain things. You got to do it. We have projects for. We do a lot of that. Next slide. On this slide, we have the actual Mantech or manufacturing part of the Manufacturing Industrial Technologies core investments. My product area, as mentioned earlier, is a Network C3 all the way over here. It's obviously the best one, but my section in there has to do with the wide bandgap semiconductors, and I will be talking about that with a little bit on the high temperature electrons. I won't go super in depth because some of the people after me who have published papers that done a lot of the legwork on that will be talking. Next slide. All right. We are heavily invested in wide bandgap semiconductors materials in the realm of RF electronics. Some of the projects we have funded include silicon carbide substrate epi manufacturing capability, gallium nitride 140 nanometer with the foundry, recently Tchaikovsky and an edge-fed growth gallium oxide substrate manufacturing capability, 250C lateral implant silicon carbide J-FET transistors, and gallium nitride epitaxial round contact. In the phase array arena, we participated in the arrays at commercial timescales, multi-chip module scale-up, along with several low-power ASIC programs, helping to develop the advanced packaging industrial base. Now, I don't have much experience with project engineers outside of the government. I came straight here once I left university. I don't know if this is the same, so I'm going to explain a little bit about the project. Right, so the government comes down, people way above me, they say, hey, we have a need. Right, so what I do, several people like me, we put together what's called a fraud area. We put online out and we say, hey, these are the requirements. Let's say, I don't know, for sniffs and giggles, socks for the Army, right? These new space age socks, right? So I have these space age socks and they have to have these requirements. So people like me sit in a room and we go contact people like those guys back on the fourth row who may have experience in manufacturing socks and research in sock development. And over bag coffee and donuts, we write up a requirements list of what the government needs in these socks, right? So then we turn around and we put that out. And it's out for everyone to see. And businesses slash Department of Defense contractors, what they do is they look at that and they decide whether they can meet that need. What they do is they send us back a proposal. These proposals come back to me, I create what's called an IPC team, individual projects. Long story short, we get together and we read over these, we look at cost, timing, schedule, what it's gonna cost, what our main strategy is. We have teams of people, this is not any one person's job. I'm in complete contact with my SOC researchers. Okay. Now, after that, our contracts and their contracts, they get together, they hash out what's going to be, how long it's going to take. And then that's when I'm involved in this because I'm going to be the technical point of contact, right? I come through and once everything has been signed and it's on paper, I track the program. We track the program to see how it's doing, what's going on, it's going to happen, do we need no-cost time machines? That's what my job is. Now, it may seem like my job is the technical, but you can't run a technical program without theoretically knowing what's going on in the program. So if there's setbacks, or you need to run up your chain of command nuances. For example, I once ran a semiconductor program where they were making something. Well, they had a fire and a flood, right? So if any of you know about semiconductor chambers, right? If you shut the power off, first of all, you got to rip that bad one apart, take the copper seals off, clean it out, put it back together, bake it down for several days. And that's if you have somebody working on it 24/7. So I have to come back and explain to my chain of command why they need more time. They need a no-cost time extension because this has happened. They can't just start it right back up. Then, you know, even after you've baked it all out, you got to do your runs to make sure what you have coming out is what you had coming out. That's my job as a project engineer. Now, I know I was facetious with the side and everything, but we have a plethora of those across the AFRL that deal in different products that do the exact same job. Now, how I'm different now is I deal with it from a manufacturing productivity, high volume, low volume. Back when I was in graduate school, I never really had to think about where my substrates came from. Are there enough substrates here? Can I get a hold of those substrates? Lead time and that. The professor said, get this, I place an order, substrates came. Now on the other side of the line, that's what I have to do. All right. These are hard charts. Next slide. So one of the gaps, GAN, like I mentioned before, it has a lot of things. GAN is further along than our gallium oxide. What we're our gallium oxide, from what I'm saying, is most likely our new GAN. It's in its infancy. We have quite a few programs that I mentioned earlier that we have out under GAN, like the 140 nanometer process that I mentioned before. We were one of the earlier adopters back when, you know, GAN was basically been used for, I guess, what, LED lights back in the past version when they first started. FRL has had a long storied history of GAN. Now, one of the things I find, so this one open foundry process, right? So we're saying we want to transfer it. You would think, right, it'd be easy, right? Open and shut case. I've got foundry over here. I want to transfer the process to. I got the foundry over here. Both of these sets of people are both trained in semiconductor processing. And it should be an easy crossover, right? Well, things happen. Stuff happens. You have to make sure, like I mentioned before, about things happen in the lab, what you're trying to do, what you're trying to get done. So you have to get that transferred over as much as possible, right? That does take time. I think this process is what, a 1 to 2 year process, guys? You remember how long? A 2-year process. Now, both sets of these people know what they're doing. There's not untrained people on either side. You're not bringing up the speed, and they both have comparable equipment. It still took 2 years to get it transferred from one to the other up to a certain level of quality. All right. I've got to speed up because I'm running out of time. Next slide. Temperature hardening electrodes. This is another section that we have in here. Temperature hardening electronics is one of the gaps we've identified. Basically, if we can fill this gap, it opens up areas on the platform that allow you to place electronics in other places on the platform besides where they're traditionally placed. But there's a problem, you know, you lose reliability, performance change, all these different things change with temperature rising. And it's not just the transistor, it's also the passive components too. So anybody that's looking for a gap to fill, we need help on hardening that. High temperature electrons are where you want to go. Next slide. Power management, we talked about this before. gallium oxide is going to be what we're heavily invested in now because of its critical field. It goes into all these low power frequency switching, high power frequency switching, kilohertz, gigahertz. All these things are very important for our RF and our power management situation. We also have had success in producing local or domestic supply in Chikrovsky and edge growth, which is, like I said, my job in the manufacturing section. Next slide. Why? Point of low power switching. The closer we can put that bad boy to the center, the better off we are. Smaller power conversion chips enabled by that high field strength that I mentioned earlier. With the fast switch envelope tracking, basically in this section you have a set amount of power that you put in, right? So anytime you have an envelope package to come through, if it's lower than that, all that power that you put, that control voltage is set there, that's all wasted. So if you can track it and make it only line up with this right there, it makes it very efficient. You want efficiency. Efficiency means less prime power that I have to use toward that, I have to use something else. Switch mode components is kind of the same thing, but it's more in the power conversion range. I don't know if you've noticed lately, they have these small power blocks that they're starting to advertise gallium nitride on. I have one in my bag right now. That they advertising the actual substrate type material that's in it. So that's something interesting coming up. That's another thing that's going to be applicable. Next step. All right, so I can't take responsibility for this. I really like to have for me. Has helped build this up. I slid in and it was made up already, but there is a huge gallium oxide community now. Pushing, investing, and trying to get domestic supply up. And you know, the movers and shakers in it right now, I think are IKZ and Novel Crystal. They're the ones who offer commercial substrates out. We're trying to get a domestic supplier up in the state so that you know our research is not curtailed by lack of access to these. Something that my manufacturing industrial technology addresses.
1 minute.
All right, doing good. As you can see, we have quite a few small businesses and universities involved in this. So this is something we don't feel like is going away anytime. We are building that up. Right now, we don't have a surplus, but when we do get a surplus, one of our main things is going to solidify the 2-inch substrates that we have got manufactured now, get them up to commercial scale, get those out. We want people doing research. Also, the high temp stuff. If you have anybody in your university in the high temp, passives or otherwise, please look us up. Next slide. Like I mentioned before, our technical needs, reliability, temperature rating, millimeter wave efficiency, our techniques, process and design to realize ultra wide bandgap and wide bandgap material, and the removal of the material. Are there any questions? Anybody project?
Are these slides going to be available?
They should be, they're distributed name. I'm allowed to release them to that information.
Thank you.
My name's Kyle Lee. You guys will notice that's not me.
I go to your next slide, I apologize.
No. That is my colleague, Mike Stearns.
Yeah.
I'll let him know this.
Yeah.
So I work at the FRL. Dr. Newton had the map of sort of the United States with where his directorate's located. So I'm just across the street where he's in material manufacturing directorate. I'm just across the street in the system directorate or RY, we call it. So, and I don't currently make thoughts, but I haven't seen my roadmap for the next 5 years. So, nobody knows the future. So I'm going to talk to you about the development we do on gallium oxide and gallium nitride electronics. And Dr. Newton and I just actually accidentally, we never met, but we discovered over email this morning how well his slides led directly into mine. So you'll see a lot of the same figures, but a little bit of a different story, a little more on the technical side, what we're doing in the labs. over at the center director. So next slide. So here, I just wanted to give an overview, sort of, semiconductor materials that everyone in this room are probably familiar with at some level. So I think we all know at this point, silicon is ubiquitous for digital electronics, and 80% of the manufacturing for silicon is in, I think, placed in 80 countries. Moving to the right, so this is moving to the right, basically increasing band gap. So second column there, we have some examples of 3-5 compound semiconductors, such as indium phosphide, gallium arsenide, which are ubiquitous for sort of low power RF applications like you have in your cell phone, things along those lines. And the United States currently leads manufacturing in this field specifically. Moving to the right, silicon carbide, slightly larger band gap. It is used mostly for high voltage power switching, and US leads manufacturing in that realm as well. Moving to the right a little bit more, we get gallium nitride, which is primarily one of the areas that our group is interested in researching, particularly for RF power, medium voltage switching. And then for military applications, things like 5G communications, SATCOM, and again, US leads already in manufacturing this material as well. And then moving to the right of that black hatched line, we start to get into what we call ultra wide bandgap materials, such as gallium oxide, aluminum nitride, and diamond. The target applications for ultra wide bandgap materials, that's typically ultra fast power switching from the volt to kilovolt range, and high voltage RF power. So the material that our group and the materials directorate are teaming up because we're interested in is gallium oxide. We see merits for that material, and we're definitely not trying to unseat silicon carbide GaN for any of their specific applications because they're very good at what they do. But what we're hoping is to find maybe an area that's right down the middle there that bridges the gap, or a niche that exists in that middle in between there, where maybe cost is a concern or extreme environments are a concern that silicon carbide doesn't have a achievements. Next slide. So I think Ben had this figure on a couple of his slides, so I won't belabor this point too much, but this is what he was talking about with the miniaturizing power switching. So this is why we're interested in moving towards higher band gap and more energy dense materials. You can make everything. In general, you can make everything. It's not that easy. There are some trade-offs, but that's go ahead. So just to highlight here up front a couple of our slides here on our gallium nitride based work, and then the bulk of my talk will be focusing on gallium oxide. But first two slides here, I just want to go over some of the work we do in GaN. So here you can see not only do we do R&D, but we do a little higher level 6.2, 6.3, what we call rapid prototyping. So we have a standard GaN 140 process, which Dr. Newton mentioned. What we do is we do the device module development for that. So here on the bottom left, you can see a 140 nanometer gate for a transistor. That process module is developed at AFRL. And then at the bottom left here, you can see a completed monolithic microwave integrated circuit. So all the process development, all the passives and transistors in that circuit were developed at AFRL. And then part of how we put the technology forward is by prototyping these mimics, developing the processes to make the yield very good, and then transfer the process to industry partners, because we are not going to large scale produce these mimics. We don't have the capability. That's not what we're tasked with doing. So like I say here, successful technology transfer to industry will enable next generation electronics. So that's how we help with the higher level GaN prototyping. And here you can see an example of we transfer our process to Maycom, to the commercial entity in Massachusetts. We transfer this process, and you can see here specifically on the right, just to kind of illustrate how well the device is performing, in this case, scattering parameters, which I don't need to go into what that means, but how well those parameters lined up. We transferred our process to their path. So we can go to the next slide. And then at a little bit of a lower level, not only more R&D level, but on more of an R&D level, we are also looking at advancing field effect transistor design and epitaxial. So here is an example of an advanced GaN epi stack called scandium aluminum nitride. Normally, a GaN 140 can be aluminum gallium nitride GaN, scandium aluminum nitride GaN. What the material stack itself allows is for you to maintain the charge in your device, but with a much smaller, with a much thinner material stack. If you can fit the material stack, you can start to scale the nodes of your device, specifically the gate node. So what I'm showing you here in the middle is on the y-axis, called current gate cutoff frequency. So that's a metric that RF planners care about as a function of gate length. So we can see by advancing our materials on wafer, on silicon carbide wafer, how we can then start exploring device design capabilities to make our devices better. And then on the right, far right, just have sort of how that scaling improves PC and RF performance. So just specifically the top left, you can see the current almost 2.5 amp per millimeter. That's about 2x what we get in a normal algae GaN count. So these are the kind of things we're exploring on our R&D side. We, in order to enable this, we do partner with industry because these materials are hard to develop. That's not necessarily our expertise. Go to the next slide. I'm at 5 minutes left, so I'm going to have to speed up here. So, Dr. Newton mentioned a little bit of this. So what is gallium oxide? It's an ultra-wide bandgap semiconductor with 4.8 eV band gap. That wide band gap is very interested in. It turns out it's the only ultra-wide bandgap material that affects. You can dope it from conductive, it's from insulating to conductive, and it has native substrates sold commercially that are grown from the metal. Just very cheap way to mass manufacture substrates. There are a couple disadvantages. No P-type doping is available, something you can see in my silicon or silicon carbide. And go ahead. So this is a brief history of how things have accelerated with gallium oxide. I won't spend too much time here, but basically the bottom line is 2013 things really took off with the first initial device results out of Japan. At ICT, they made the first transistor, and then into the 2014, 2016, AFRL kind of took over. We had the first record-breaking device results in gallium oxide. Highlighted here at the bottom right, my colleague Andy Green demonstrated a 3.8 meter breaking field strength, which is the highest, was at the time the highest ever recorded in a lateral transistor. It's since been beaten, but by gallium oxide. Go to the next slide, please. So one thing that people talk about when they're talking about device engineering is bonds or figures of merit, but the problem goes a little bit deeper than that. We can say that we want to get to R-on and break down one, but one thing that people don't consider when they're benchmarking that way is cost. So this is one of the main things that we see as promising for gallium oxide is, like I mentioned before, the growing from a metal makes production a lot cheaper. So you can see here all the way to the left, that would be diamond and silicon carbide. Those have to be grown through what's called vapor transport, which is the tools are expensive, the process is complicated, which makes the product expensive. So we see this as a major win for gallium oxide. We think that the other problems can be engineered out. Go ahead. So just to not belabor this point, but just to kind of give a little bit of perspective, this was a paper written by in 2019, basically projecting the cost per wafer for a 6-inch gallium oxide wafer relative to silicon carbide. You can see already without any process improvements, we're already at 30 costs. And again, this is a projection. So then on the right-hand side here, I have listed here what the commercial producers of gallium oxide, who at the time this data was taken, they were the only one selling gallium oxide. So one company in the world selling gallium oxide substrates, and you can get a 4-inch for $5,300. I don't know what the silicon carbide substrate costs. You just buy it from 2.6 or something, but it's not much less than that. So you already see the benefits of the ease at which the substrates can be grown, even this early in the game, when only one or now 2 companies are operating. We can go to the next slide. So there are a couple, as Dr. Newton mentioned, there are several groups pioneering the materials research and device research, gallium oxide. Here I'm going to highlight the materials research. So NTT, as I mentioned, they kind of got the ball rolling, and then AFRL within NTxSI in Germany, the FOSR, what that acronym means is state and R&D, research and development. But and currently AFRL RX has the most advanced gallium oxide epitaxial MEE tool in the world, capable of doing 4-inch epitaxial prototyping gallium oxide substrate. We can actually buy 4-inch gallium oxide substrates and grow them. Next slide. Speaking on devices specifically, so we do a lot of device work at AFRL, but there's also just in Ohio State does a lot of pioneering work in gallium oxide devices, as well as here at the University of Utah, based in UCSB, Schuram Murphy. And then internationally, in Germany, FBH, and there's a lot of device research going on in China as well on gallium oxide. We'll go to the next slide. So this is just highlighting a few of what I would call milestone device results coming out of AFRL. Along the top here is the more technical result, and along the bottom here in the gray boxes is kind of how that corresponds to programmatic investment. So just a couple highlights you can see as I mentioned over there at the far left on the bottom. As soon as they influence our invest in IKZ to get us good epi, we start making the world's highest electric field transistor. So really it's just a matter of which we're working with NCT IKZ internationally and then our domestic substrate producers to get us the material. Get us the material, we can make these devices. So that's just the main highlight. And then more recently, just for the interest of time, I'll skip this stuff in the middle, but all the way to the right. Now we're really working on analyzing how these devices behave in a real world application, and looking at things like extreme environments, rad hard capabilities, high temperature capabilities, and things along those lines. So I've got 3 more technical slides at the end that I can skip in the interest of time. So that's all I have. Thank you for having me. If there's any questions, I can answer.
Did we ask questions?
Oh, yeah, sorry.
Yeah.
Sorry.
Go ahead. What kind of turn on voltages do you get with these FETs?
You need to speak up.
Oh,
everybody.
yeah, what kind of turn on voltages do you see with these kind of FETs? And do you design them to work at room temperature or just at high temperature?
So we design them to work. We design them to work at room temperature primarily. I would say in the last couple of years, we have started taking high temperature operation in mind. How do we? What materials can we make the electrodes out of? Make the dielectric out of that at high temperature. The turn on voltage question, that's
Just roughly, are we talking in the 1 volt range, 10 volt range?
it's a complicated question because it's as I'm sure you know, it's a huge function of the epi. So I would say to this point, it varies a lot. I would say -20 to -5, roughly. There have been some demonstrations of recess fitting the channel to get E-mode operation. That's all kind of. I would say in general, for the devices we make, it's about -20 to -5.
So
We have a brief question from the chat as well, real quick. Is anyone looking at how GAO etches?
How it etches, we can etch it very easily. So yeah, I mean, early on, we had to develop recipes to etch it, and I think that's, you know, again, it's a complicated question because I don't really know what, you know, what application the person asking has in mind. But in general, we can etch gallium oxide.
So I saw the bowls of the different materials you're working with. So that tells me you need crystalline material.
Yes.
Have you looked in using amorphous materials to try to make devices? The reason I'm asking is I make ceramic matrix composites. Some are sick, you know, silicon carbide, reinforcement silicon carbide. I was wondering if I could like engineer the electronics directly into the structure. But that's going to be an amorphous
I would say
state.
amorphous gallium oxide would not be good for any device applications. Okay. Thank you.
Thank you.
Hello, everyone. I'm John, Central Favorite, today I'm going to talk about high temperature electronics parts that we started currently. Now that so in our lab, as I was demonstrating, mostly was on high power communication. But in the last few years, we have started exploring the capability of these devices and just not only to understand the capabilities of the existing devices, like the state-of-the-art devices, but also to define the future devices. So why do we need to talk about high temperature? So in AFRL, we are interested in hypersonic devices, developing electronic devices to hypersonic. And depending on the speed, altitude, or angle of attack, the temperature distribution around the body of this aircraft will be very high. So this is the temperature distribution that is shown for the X in NASA. And you can see that some of the temperatures in some parts of the body, especially the most zones and the areas, are 700 C. And in addition to this one, there are also other decoys that are actively used in aircraft solutions that are shown in this radium image in the top middle. These decoys are used for redirecting the missiles away from the aircraft, and these are generally driven to very high power. So for all these applications, you either need to design electronics that will be compatible at the temperatures that you want to place the electronics at, or you can generally design some insulation to reduce your temperature as well. So next slide, please. So in addition to the hypersonics that is shown again in the bottom right, so there are other applications of high temperature electronics. And depending on the application space, the temperature range that you need to design your electronics for varies. Like for example, breeding requires a temperature maximum temperature of 200, your application 300 or more. These days, it is getting more and more higher. So for turbine applications, space applications, you need to design electronics that at least are compatible up to 500 C or more. Next slide, please. So if you currently look at the current state of art, transducers like pressure transducers, temperature transducers that can operate at very high temperature. That's not a problem. The problem is with the electronics. Most of the electronics are based with silicon, gallium oxide, indium phosphide, and these are more designed for operation at low temperature with a wide performance rating. So in collaboration with in support of DARPA's and the recent efforts that is came up to the recently in ARTS program. So we are working with them to see whether we can enhance the capabilities of electronics so that they can operate at high temperature, so that we can combine all this transducer and electronics together, and so that the entire system works like at horizon that is required. So in terms of our interest, as like the previous speakers have demonstrated, we primarily are focusing on gallium nitride and gallium nitride devices. So that's what we have been historically supporting national and international efforts, and we are pretty good at that. So we will see how these two technologies are relevant for different. So this is an overview of our current high temperature electronics program. The program initiated back in 2021. So I leading with the previous presenter, I got some initial seeding funds internally. So we like use that money to purchase the oven and just placed our electronic devices in the oven and cooked it. And we just saw how this device behaves. So we cooked it up to 500 C and just tested the device performance. And eventually, over time, we also collaborated with other companies, other academias like University of Illinois. So we went there, we took our devices there and tested it in a more sophisticated workstation. We saw that the performance like something similar. And these initial results allowed us to like invest, like the convince AFRL and DARPA to invest more. And recently we have purchased more sophisticated equipment that can not only do DC measurements that we were doing before, but also can do some RF. So we have in the process of installing the equipment that we have now. So overall, our plan is to like expand this program. We have like a long 3 to 5 year plan. I will continue to support DARPA in the current programs that they have developed, and we will hopefully like initiate any new programs that might be coming up. In addition, we are also collaborating with different industrial bases, different companies, and also academians to like form this thermally hardened microelectronic portfolio that we are starting for. Next slide. So let me go into a little bit technical, like what electronic system we are talking about. In our lab, as Kyle and Ben was talking about, we mostly focus on like developing devices that offers like higher efficiency, higher range. That goes into systems like decentralized systems like Skyport. So if you are not familiar with Skyport, this is a Vanguard program from Air Force. So it is mostly not only used for like increasing the coverage of aircraft, but also it is it requires like a involvement of lot of communication between these different components of the aircraft. So there is involvement of AI, there is involvement of like there are requirements for synchronization between different AI components. So, and all these things require you to design devices that not only has high power, but also has low size, low weight, and like low cost. So that's the top C requirement that is coming in this way. And for all these devices, in all these devices, there are electronic components like transmitter, receiver that is shown in the block diagram here. And this transmitter receiver is mostly used for enhancing the signal strength so that you can communicate between all these components. And one of the key components of the signal, like transmitter receiver, is the power amplifier that is shown in the block diagram here. And like the power amplifier can operate at different frequencies. So you need to increase the efficiency of the power amplifier, but also want to design the receiver converter so that you can like track the signal so that it operates more efficiently. Next slide. So one of the key components of this electronic is the transistor, and in a transistor you like have scattering carrier moving from one terminal to another, and that kind of dictates the performance of these devices. And this triangle that is shown here, you want this triangle to be as big as possible. But what happens is as you are going to high temperature, the scattering increases. So the next slide. So the triangle gets squeezed. The performance of the device goes down. So we have seen this behavior in our currently traditional 140 nanometer devices that we have tested. So the question is whether we can do anything better. Again, this. So we selected some of the devices that have been scaled down significantly. The scattering of carriers gets significantly reduced. And as a result, the performance of the devices over temperature do not scale down that much. But the problem is these are really many miniaturized devices. These are not that much reliable. So we have to really work with defense industrial base and within our lab to improve the reliability of the devices. And then another thing is we also have to improve our test capability because we see that like the testing for this particular case was done up to 200C. We believe that it will not like maintain its gain at as we go to high temperature because the scattering length reduces as you are going to increasing temperature. So the 40 nanometer gate length that we have used for this particular measurement, it is good for the scattering length, but as you go to high temperature, scattering length will go down. So the 40 nanometer will not get. So in addition to the GaN-based power amplifiers, as the previous speaker said, we also work on gallium oxide-based devices. And I will not repeat the things that they have already mentioned, but most of the things that I want to, the main thing that I want to mention is the gallium oxide is a manifold process. This is the only wide bandgap semiconductor that has manifold capacity. That's why the cost can be predicted very low. And when you measure the performance of these devices at up to 500 C, the performance will not degrade that much. That's what we have seen in our initial devices. So we are planning to advance our technologies further and like to improve the performance. So the current level in our devices is still not to the level that is required for designing power converter. So hopefully in future we will improve the power on our power like device current and test power converters. Thanks. So this is the last slide. This is kind of the like going from device to prototyping and to process to technology transfer is kind of the motivation that we want like focus in our lab. Like we like for example for the GaN 140 nanometer with NTx, we have worked on like initial device demonstrations by taking technologies that were developed in the universities. We improved the process. We develop process development team. We are focused on improving the reliability by working on fundamental aspects like contacts, doping, mobility improvement, and direct integration. And that enables us to do technology transfer recently that we have done with NACOM, that's a commercial foundry, and we also did with defense industrial base like BAE and CASE. So we want to do something similar for high temperature GaN-based electronics. For high temperature gallium oxide, the story is a little bit different as the previous speaker demonstrated. We started working on like at the very low TRL level. We are still improving our device capabilities. Will hopefully enable like our current work will hopefully enable us to demonstrate multi-kilowatt power switches that we've tested like different frequencies and different temperatures. So overall, like the process to technology transfer, developing this process to technology transfer pipeline is the overall goal of our project. Thanks.
How does your tech transfer pipeline work?
How does your tech transfer pipeline work?
So the way that it works is initially we look up like across, say for example, Wikiniverse or across like the world, like the for example for GaN 140. Back in 2000, like many research groups are working on like low TRL level devices. Then we took that like existing technology, bring it to our lab, improve the TRL level to say 4 or around 4, and then we like develop a process development team. And that process development team we collaborate with NTx. So NTx kind of like brought me some of the commercial foundries that brought in from some of the commercial foundries like NACOM. And then NACOM, we transferred the PDK to NACOM. Then we did a co-development for 2 years that Ben Newton was talking about. And after 2 years, we kind of compared the performance of our devices versus their devices, and then we completed them.
I'll just comment on that. You know, the level of like transfer, sometimes it's just a process module, sometimes it's you know, full blown transfer, sometimes it's funded up with your Mantech. There are many different levels of engagement depending on, you know, where the boundary's at. So it just yeah, there are many different vehicles that we can transfer this technology that we have in our lab outside.
and level of interest.
Thank you.
So do you license that to all of the foundries? Or is it just working with one foundry?
We're not licensing. We
Just
just
giving it away?
give it away.
Yeah, we don't get any
For rapid insertion.
Our tech is free.
Our tech is free. We're open book.
Yeah, I wish.
I mean, free.
Thank you.
This is great. I didn't coordinate with the census director folks, but this is dovetailing nicely into a story. So my name is Josh Kennedy. I sit in the Materials Manufacturing Directorate, which is on the same side of the street as Ben. And so I am going to talk to you a little bit about, so Ahmad and Dr. Liddy talked about that advice work. In the Materials and Manufacturing Directorate, I sit in what Ben referred to as the in-house research side. And so I'm going to talk about how we pull things a little back to kind of fundamental material property measurements and developing new materials, but for the same kind of application space we've already heard about today. So next, please. So again, I'm in the Agile Electronic Materials and Processes Research team. We have about a dozen government SMEs and about 30 or so on-site contractors working across three main thrust areas. The first one being, as you've heard about already, wide bandgap semiconductors. So the picture earlier of the GOX NBE system sits in our labs. And we have a couple of people who really make it their bread and butter to understand the MBE growth process for GOX, to include, how we think about different doping strategies, gradients, how we think about the incorporation of novel oxides to form the, high voltage gate barriers and these materials, but at the fundamental level. And then, of course, we do have work also in Algan and Alscan. You've heard these already today. We in our lab really try to understand the fundamental material science of the growth process in those cases. And then we do a little bit of what I would call early stage device design and prototyping, but really we rely on the sensors folks for most of that. As you've already heard, the main application area for those materials currently is power electronics, to include high power RF, and there's an emerging interest in pulse microwave power as well. The second thrust is this tunable heroic materials. So when we think about filters for RF systems, the current tunability comes from the ability to change a magnetic field using a relatively large electromagnet. And that is prohibitive in terms of size, weight, and power for a distributed or small scale system like what you might want in an actively scanned array. And so we are developing novel heroic materials, namely 2D and thin magnetics, where you can tune the magnetic properties through things like magnetostriction or surface acoustic waves and things like that. And so we developed some approaches to doing tunable filters by changing the local magnetic properties of very, very thin films in our devices. And then the last one that I'll talk about actually mostly today is where the majority of what I'm going to talk about with respect to high temperature comes in, and that's in computing. And so we have a burgeoning interest in high temperature computing. This is certainly driven by some of the demand signals that you've already heard about today. But the competency and the capability that we're bringing to bear against this problem space really builds on a long history in computing architectures. We work in emerging neuromorphic materials, We actually have a strong investment in low dimensional semiconductors, 2D semiconductors for ultra low power switches for things like, remote platforms with limited energy budget for the computing side. And we're leveraging that now to look very seriously at the needs for high temperature computing. This diagram here, it kind of shows what I was saying earlier, that basically, while we touch on some early prototyping, really the focus of our competencies is in the thin film growth and characterization. Next. So we've already heard about this a little bit. I want to foot stomp this a little bit. There is a growing and I would say multi-domain and use that is both commercial and DoD demand for high temp computing. You've already seen some of the diagrams in the earlier presentations about places where some of these electronics, we would like them to be, that we just can't get away from the temperature. There are two things I want to emphasize here. We are primarily interested in new materials that can operate through those temperatures, those elevated temperatures. Clearly, there are other engineering approaches to deal with thermal management, but we're really concerned with those few cases where thermal management just isn't an option. You are soaking at some temperature of 200, 300, 400 or higher, depending on the application space. And that includes things like engines, vehicles that are going very fast. And then down in the bottom right there, you see there is a strong commercial pull for this out of the oil and gas industry, as well as to some extent in the automotive section. It's already been mentioned, cost solutions are pretty much limited to 250 C, and really for the majority of things in the computing sector, it's really about 100 C. Next, please. So if we think about the overall anatomy of a high temperature electronic sub-assembly, Ahmad talked about the RF and power conversion elements, but there really are a lot. Ben already mentioned the passives, the packaging. We're trying to take a holistic approach. And so to that end, we because of the competencies that we've built over the years in the materials and manufacturing directorate, we've really focused on two things. So one is the packaging. So we're working with, and I think I showed this on another slide, but we're working with both small businesses as well as the manufacturing institutes to look at materials for how we integrate these various subcomponents in a way that is enduring high temperature. In the active component side, for computing specifically, what we've really identified the critical technology gap that is future looking. Okay, so you've already heard about the work in silicon carbide. We're familiar with all the things going on at NASA and GE and silicon carbide logic, certainly some exploratory work in GaN logic and things like that. But over the past year and a half or so, thank you, we've really identified that as we move into a fully functional microprocessor, non-volatile memory is a key limitation at high temperatures. So we've chosen to focus strategically on that. Next. So to that end, and this has already been talked about, so I won't belabor it too much, but really we sit at the nexus of our industrial, small business and academic partners. We try to make connections. We try to do internal IV&V, and then of course we try to lead in the development of areas, technology areas where we see that need. And you can see some of our partners specifically in this field of high temperature computing here on this slide. But for the sake of time, if we can move to the next one. So one of the things that we do is in-house testing of these systems. So we have a test rate that can go up to about 650 C. We can measure switching and retention at sort of DC to low megahertz sampling rates. And then I'm sure that RY is building up a similar capability at higher frequencies. But this is something that we've been exercising recently and already seen the value of. Next, please. And so on the high temperature memory side, there are two memory technologies that we're particularly interested in, that we're bringing in-house to look at. One is something that I think several people in the audience are already familiar with, a company in Texas, Surf Labs, that's making this carbon doped oxide that we're very interested in the capabilities of. And then another is a technology out of University of Pennsylvania that involves ferroelectric switching as the memory element. And in both of these cases, the fundamental switching mechanism is robust to temperature because of the material properties. So those are the sorts of things that we're really interested in pushing in the future. Next, please. I think that's it. Great. Happy to take any questions.
Did have one. The last speaker, but I'm sure you can probably. What is the carrier mobility of GA203 at 500 Celsius?
I'm sure I cannot answer that. Mobility at 500 C, I don't, have we measured mobility?
We have measured it, so it's around 20.
20.
So, is anybody considering hardening these technologies while you're?
Hardening.
Well, I mean, just what is the response to like natural radiation?
Oh, radiation hardening.
Yeah, so neutron.
It has not been a strategic focus for us in our group. I was having a conversation earlier. There certainly are DoD funded efforts and AFRL funded efforts in that area. Or if you're asking specifically about the wide bandgap semiconductors or the high temperature memory.
You know, if you are talking with Citra, it might be a good thing because that's when I was there, that was their #1 program in that agency. I would just begin the conversation with them because for a lot of the applications that you're talking about, it's going to be important.
Yes, thank you.
Oh, yes. So do you guys have any activity in the wide bandgap for diamond, or is it?
It depends on what you mean by activity. So we invested in some thin film diamond growth several years ago and more or less abandoned it. I think it's on our radar for sure. We can imagine applications where the properties of diamond would be attractive if we could grow thin film single crystals in in a foundry compatible way.
Thanks.
Any other thoughts?
Yeah, I mean, I'll just say there are some major intrinsic issues with the material we use as a semiconductor technology.
Yeah, no, I agree. I know, for instance, ARL, I think has some significant activities in diamond.
And so does the NRL.
NRL too, yeah.
So it's got an ARAP and they're developing that, focusing on gallium oxide. Yeah, there are some issues that scare me, so I spray it.
I mean, when you show that you get 2 millimeter substrates,
That's right.
it's hard to scale.
That's right. That's right.
So I realized I'm gonna have to retake a photo. I'm nearly as serious. Thanks, first of all, thanks for having us here, to talk to you a little bit about Starry Night. I'd like to thank the Wright Brothers Institute, University of Texas, at Dallas, and also AFRL, for the fantastic collaboration, between our organizations and SWC Crane, and the labs here. So with that, let's get started. Next slide. So over on the right, you'll see sort of an organizational hierarchy of the superior programs beneath which Starry Night exists. I'll call your attention to Dr. Deb Fenoy at the top. He is the Principal Director for Microelectronics for the Office of Undersecretary of Defense for Research and Engineering. Beneath them is Dr. Matt Kay, who runs the Trusted and Mature Microelectronics program for Dr. Shenoy. And then beneath Dr. Kay are Dr. Joshua Hawk and Dr. Darren Crum, leading the RF and optoelectronics technical execution area and advanced packaging and test technical execution areas, respectively.
The mission of the program is shown towards the bottom of the slide. Two sort of key objectives here are to improve access to and assure state-of-the-art RF gallium nitride and integrated photonics manufacturing capability domestically. And also develop, demonstrate, and transition state-of-the-art devices and intellectual property via prototyping in a very open sort of way. Next slide. The capstone projects that exist within the RFOE and the ABT TIAs are shown on this slide. In the interest of time, I'll skip over ship and steam pipe, which exists within the advanced packaging and test technical execution area. And instead highlight the RF and optoelectronics capstone project, Starry Night being the first shown in green, which seeks to mature millimeter wave GaN foundries and advanced interconnect technologies, partnered with Hughes Research Lab, Northrop Grumman Space Systems, and Qorvo. Kanagawa is next. It seeks to mature optical I/O chiplets and lasers for insertion into multi-chip packages, particularly for data transfer applications. And then Eclipse is last. It matures advanced materials for insertion into millimeter wave components. Next slide. So this is our problem, both commercially and within the Department of Defense. And so it should be very obvious that this problem is very complex. We have a very congested environment. We require very high bandwidths and throughputs in our communication systems, whether those communication systems are commercial or for DoD applications. Data traffic demands are expanding very rapidly, approximately 70% per year. And we've seen some very aggressive throughput requirements for edge compute, for example, on the order of 200 gigabits per second or more, and for AI applications exceeding 2 terabits per second. Within the DoD, I'm skipping over some material in the interest of time here. We have many different interconnected systems that have to share a lot of information. So you think of high resolution imagery and ISR sensors and payloads. We need to move that data in order to make good decisions on the battlefield in a very rapid fashion. So applications such as remote sensing, radar, imaging, security screening, datacom, telecom, command and control messaging, all are driving requirements for agile waveforms, low size and weight solutions in these different types of systems, and high power capabilities to stretch that data over long distances. Next slide. At the top of this slide, we show a simplified decomposition of an RF communication architecture. You'll notice that the RF front-end module, which is sort of the transmit receive hardware that provides wireless communication, is highlighted in green. Additionally, we've highlighted the optical interconnect in orange. The Starry Night program is primarily focused on the green box there. Kanagawa, for example, focuses on the orange. The other graphics on this slide show how higher frequency devices operating at higher powers are needed for our applications, and how GaN mimics, for example, and front-end modules fit into that space. And then the graphic on the right shows bandwidth density versus the interconnect distance for optical data communications to enable edge computing and AI sort of applications. Bandwidth density being sort of the, let's see, I can't even read my own writing here. The throughput divided by the size of the device that's providing that transmission. Okay, so Reduction in swap is a theme that you've seen like across all of these presentations, right? In AESA radar systems, for example, or communication apertures, AESA is being active electronically scanned arrays. We know that we need more compact assemblies where we can operate with them smaller arrays, but smaller arrays sacrifice gain in the apertures, and so that smaller envelope of the actual aperture drives a requirement for increased power in our actual RF amplification devices. So that's kind of highlighted on the left graphic. And then on the right, we show how requirements for DC power and heat generation decreases as a function of amplifier efficiency. Why do we have to care about that? Obviously, in many of our applications, we're power constrained, but also heat is a major driver of reliability in a lot of our systems. So as you make your devices hotter, they're not going to operate as and so with that, let's kind of shift our focus a little bit towards gallium nitride, which we expect to provide millimeter wave performance, driving down swap, increasing reliability, and ultimately, our hope, decreasing cost. So the next slide shows like the rich history of investment and development in gallium nitride technologies for RF applications. This timeline actually starts a bit late. We know that these investments began well in advance of 2000. But partners like DARPA, ONR, Office of Naval Research Laboratories, and AFRL have all been major players in the maturation of these semiconductor devices. They have been inserted into DoD systems like the Air and Missile Defense Radar and the Ground Air Task Oriented Radar. They've leveraged programs like DARPA Next, developing nitride-based FET technologies, DARPA and maturation programs to ensure onshore manufacturing capabilities for millimeter wave GaN. The DARPA Dream program, which enables progress in novel millimeter wave GaN structures and improve GaN heads for low noise and high power amplifier applications. And then the AFRL Sensors Directorate has already mentioned, I believe, some of their transition of processes developed locally into other commercial lines. And then finally, we arrive at Starry Night and Eclipse, which continue to enhance manufacturing readiness levels of domestic millimeter wave and material sources, boundaries, and advanced interconnects. From MRL levels forward to about 7. Next slide. This slide shows where application spaces map to sort of like a power and frequency space. So I mentioned earlier the importance of high power at high frequency, and you'll notice that defense and civil radar, SATCOM, and backhaul are all sort of occupy those spaces. Some of the strengths and weaknesses of GaN technologies are also shown on this slide. Next slide. So the key elements of Starry Night are shown here. This is a little dense, so I'm actually going to read through this with you. Task A addresses manufacturing maturity of state-of-the-art GaN technologies by funding 3 foundries, transition technologies from MRL 4 to 7. Task B addresses the need for innovative GaN and NTxSI by funding access for onshore defense industrial base, academic and DoD groups through multi-project wafer runs in each of the Starry Night performance teams. These designs are created under government purpose rights and saved in IP repositories developed by the foundries to enable future DoD programs to access and evaluate potential designs for their programs. Task C bridges the gap between device and packaging areas of the supply chain by maturing advanced interconnect technologies. This allows Starry Night GaN technology in a flip chip form factor for easy integration into the advanced packaging ecosystems. Next slide. This slide shows a schedule of opportunity, essentially, for design into a variety of gallium nitride foundry processes. So the box I'd like to highlight, which you can't read all the way back there, is our next application submission deadline, which is the 27th of September. For more information on the requirements for proposing into these production opportunities, please see the URL that's at the top of the slide. Next slide. We've already kind of talked about this one, so let's skip this one. And we'll come to our summary. So we've talked a little bit about the commercial and DoD application needs for advanced sensors and communication systems, and how those are driving higher frequencies, lower bandwidths, and lower latencies in all of our systems. Active antenna systems have reshaped the RF front-end ecosystem. The next transformational technologies are going to be wideband amplification, switching, and adaptive filtering. RF band provides discriminating millimeter wave performance, which impacts systems, swap reliability and costs. And then DoD investments provide domestic access to mature millimeter wave band processes. So again, the thing that most of you will probably care the most about in this presentation, that URL at the bottom of the slide. So take a note on that. If you have questions, you're certainly welcome to send those my way. But Mr. Vince Williamson is also in the room. He is running the Starry Night program for the TAM portfolio. Thanks for your time.
I have just a general question for yourself and also for any of the AFRL speakers. We've been hearing a lot about non-technical question. We've heard a lot about the workforce need, silicon-based microelectronics. I assume you guys are feeling the same kind of push. This is probably also mostly PhD-driven work that's going on right now, not the faculty level technician. Are you able to meet your workforce needs? What does it look like for the future for PhDs? Do we need to be pushing more into the pipeline? What's the general census?
So that's a great question. Scarcity is certainly a problem there. Another challenge that we face as a DoD organization in the recruitment of talent directly is limitations related to compensation. So partnership with industry, with academia, trying to steer really top talent into like our DoD prime collaborators is a really important thing. And beneath the TAM structure, we are making investments into academic programs, funding faculty time and research assistant time for advancing design in these types of devices. So we absolutely see challenges there.
We've got programs reaching as low as elementary school, so, but we'd like to do more.
Yeah, it was like the DoD labs themselves, like NRL, FRL, are they having trouble recruiting? Or are they finding?
So one of the problems that we see, because we cannot hire anybody other than US nationals,
Right.
and within US nationals, there is a lot of drive for students moving towards software related projects rather than hardware or micro fabrication, microelectronics related projects. So that's something that we have to work with, like increasing incentives among local students, maybe financially, maybe some other way.
And also competing with the salaries of Intel and things like that's gonna be a challenge. So curious how you're going to attack us.
There's a lot of internal workforce development that's happening, because sometimes we can't go out and effectively recruit or compete for that talent at an experience level. So we'll start with graduates, new in the organization, master's degree personnel, and really invest in their continued academic development.
To your question, sir, there's a program, there's several programs that they have. I was part of the SMART program. It was a program where you were funded through your academic matriculation, and then you were given a certain amount of time to go fulfill that Department of Defense area, and you work toward that. So they have programs like that, feeder programs, where you try to go in, and then hopefully after so many years, you decide to continue your career with them.
The board application call, I believe, should be opening soon. That typically closes around the beginning of December. We'll fund recruitment candidates tuition and provide them with a stipend. For retention candidates, I believe it covers approximately 30% of the employee labor and also funds tuition. And there is a continuing service agreement that goes along with that, so it keeps that talent in these DoD organizations.
Is a smart targeting undergraduates or grad, what is smart targeting?
I did it for graduate school, master's in PhD, but I think they may have undergraduate programs for it now. When I first started, it was mostly graduate programs, but it's become extremely competitive because it's been around quite a bit and it's going out.
Yeah, just the last couple of years, AFOSAR has gotten involved in secondary. And they're considering primary. So they've got a person who sits in that, so you can talk to the chief scientist. And you can also talk to the person who's in charge of special programs. So Anthony's a good person.
Thank you.
Thank you.
You can smart.
Thank you for the organizing this. Thanks to Danny and Snap for all the help and support to make it happen. So we're gonna move to the next sort of the stage of this collider. We're gonna talk from the academic perspective. Okay, so also has to present some of the UT Dallas research capabilities. My name is Manuel Science and Engineering at UT Dallas, and also working with a great team here on establishing this center for harsh environments, semiconductors, and systems. So what I'll do is, I'll go to the next one. What I'll do is I'll tell you first why are we so interested in this area, on this aspect at UT Dallas. So this shows just a busy slide, so it's a Google Maps slide. But what I want to show you here is sort of where the jobs are in Dallas Fort Worth, okay? And what UT Dallas is with respect to that sort of job density within that area. So on the left-hand side, what I'm showing is basically where UT Dallas is, about a little here. So we are right there. And those anything you see here, these are paths. So this is Orbo. We just, some people talk about Orbo. This is a 300 millimeter path from TI, actually two of them, they just went to an extension. These are the original location where TI had the original paths, and they have at least 3 or 4 in there. So we're very close to them. Then this color there shows the density of jobs. So we're right there at the epicenter where all the jobs are here. So that academic institution needs to work developing a strategy to be able to provide that workforce needs while also helping with our mission of research and development. Now, everything happened up to last year, roughly across us. Then TI decided to open 4 new paths from Germany. So that within an hour and a half of UT Dallas. So we have to help meet all those workforce development needs for TI, but all of these little dots here are companies that support all of these microelectronics ecosystem in the Dallas Fort Worth area. We're right there with a lot of this action is happening. That's why a couple of years ago, through our VP for research, we decided to come up with a strategy, right? How do we start putting together the federal efforts at UT Dallas to be able to meet all of these corporate development needs, while also being strategic about what research areas we should be focused on. That's what we decided to do and start working together as a team. Go to the next one, Jim. So we decided to sort of capitalize on a lot of the expertise that UT Dallas has, one incredibly large sector. So these are some of the centers that have graduated, except this one infusion, that sort of help us become more and more specialized, or enable to have more faculty, grow our infrastructure in microelectronics, in nanoelectronics. So most of you are probably familiar with a few of these. This is kind of unique. This was a partnership with Korea. So fusion is fusion semiconductor, commerce, and intelligence. So that was a 10-year or so program, very successful, that we had at UT Dallas. And once we graduated, then we created the infusion, now the international fusion semiconductor commercialization that is ongoing right now, also very successful. So we are not strange to running large centers and programs. So we use this expertise, this knowledge to build what is coming next for us. I'll be showing you this slide. The next one. These are other centers that are relevant, that are current at UT Dallas, that we can use to perform a lot of the effort, a lot of the infrastructure, a lot of the strategies that we are developing. So we have a center for quantum centers, work in a lot of quantum computing in there. We have applied artificial intelligence in learning. This is one of our most successful centers, the Texas Center of Excellence. I'll tell you a little bit about that center later on. We also have centers that are not necessarily microelectronics, but benefit from progress, benefit from microelectronics, like this Texas Biomedical Device Center. And very important, right? Something that we haven't mentioned yet. We have to make sure that we can bring all of this together to innovation and entrepreneurship. So we have all of those centers there that make a great ecosystem within the university to support a lot of the research that we are as institutions are doing. So we go to the next one, please. So facilities that we have to support a lot of this work. So we go to the next one. So the first thing that I want to bring up is our clean room. So we have state-of-the-art clean room. So I don't know, it's a 300-millimeter wafer, 4-inch wafers. But the view of this is that this is modeled after sort of an industrial clean room where we have sort of thermal diffusion, we have lithography, we have thin film, edge, characterization, and so on. We can run a lot of processes in this clean room. If you go to the next one, I'll show you what I mean there. So these are just some examples of processes, devices, the prototype that we have been able to run in that clean room. So on the top, what I'm showing is, for those of you that are familiar with device fabrication, what I'm showing there is how we develop the process all the way from the concept to having the device. On the left, on the top left, what I'm showing there is a single device, one transistor, fabricated transistor. Then what we do with that transistor is to go and extract a model that I can use later on to create a circuit. Once I have the circuit, I can go and build the mask. And once I have the mask built, I can go fabricate that device. And so everything that you see here, we can do it there like we did. Now, this is great, but this may be useful to test particular material, maybe a process and so on. But you do also see integration, right? So for those of you that are familiar with microelectronics, we rely on CMOS, right? You have to do PMOS and NMOS, and this is a 12-mask process also run in our clean room there at UTD, where what we show is a polysilicon CMOS, where we have a N-type and P-type device together. So what I'm trying to show with these two examples there is that we have a clean room that is capable of building multiple mask levels with acceptable technology. The other thing is, besides the clean room, we have other sort of facilities around the clean room that we can use to fabricate this kind of prototype. So this is the prototype that we built for DHS, right, that Dr. Gene and I had, or I still have with the Department of Homeland Security to develop radiation detectors for neutrons and gamma. So we developed both neutron and gamma detectors fully together. This is a 4-inch wafer that we fabricated in our clean room. Again, showing all of the sensors in there for neutron, some of the construction that we have mentioned here. So we put all of those together, along with what these are the neutron detectors. These are
the camera detectors, put it together. We build not only the prototype, but also the app that connects to this prototype, so we can connect the network, multiple devices, so we can track any potential radiation threats or potential radiation conditions. So not only devices, not only materials, but also we can do a prototype, which is kind of unique. So that, if we go to the next one, that will hopefully help us come up with better ideas, as I will show next. But just having where to build devices is not enough. So we have to be able, as some of the earlier presentation showed, we have to develop new materials. And to develop new materials, we need to have slightly sophisticated material deposition, synthesis system, but also characterization. So what we do is we rely a lot on the materials, the condition material synthesis characterization capabilities that we have at UT Dallas to be able to feed that information, to feed those materials down to Houston. So the way that I picture this is like our R&D in our labs, it's our faculty labs. Whenever they have a good material, good process that they want to test, try in the clean room, we send it down to the fabricator, right? So we can collaborate with faculty and do process development and design. So we have, you can see our faculty is very happy. Happy with the lab. Go to the next one, please. So materials is one thing, right? We also have, as you know, to rely on modeling information. And we have clusters of faculty that do all the way from what you will expect, ab initio, right? Modeling, simulation, to materials design, like thermodynamic methods, computational machine learning, and so on, to develop those materials. We also have a very strong team that does a lot of device modeling and simulation. So not only material model, not only like ab initio simulation, we also do materials design, with those learning from the modeling. Once we have the material, we can work with the guys that do device modeling. So that will be covered all the way from fundamental to the device modeling. So that's, and we don't have like a single faculty, we have about 4 or 5 faculty on each one of these clusters, and they're all across from electrical, material, and so on. So I'll give you a couple of examples of centers that we have and what they do. So this is the center I was telling you earlier. It is one of the most successful before the Center for Fashion Environment came in. So this is the most successful. Hopefully, next year we'll say we are the most successful. For now, NTxSI is the most successful. They do a lot of work on analog designs, okay? But they don't do prefabrication at UT Dallas because they use state-of-the-art CMOS technology, right? So we don't have that at UT Dallas. So what they do is they spend a lot of time doing the design, and they send those designs out for fabrication to Moses or X-Lab or whatever foundry will do the fabrication. They send it back to them, and they go and do a lot of different work related to their devices. So if you are interested in any type of analog design, any type of analog related application, Professor Pino is a worldwide expert in this field. Probably on it. And he has collaboration all over the US. So it's a very successful center, and it's kind of uniquely funded. So there is some direct funding from TI, there is some direct funding also from SRC, because some direct funding from UTD, besides all the external funding that this center will bring. So the next center, we go to the next one, please. So we combine, or Yorgos combine NTxSI's expertise with his Cybersecurity Research Institute, with his institute, which is the Center for Hardware and Embedded Systems, to create this effort. It's called the Trusted and Reliable Architecture Laboratory. What it does, or what Yorgos does, is he works about 2 major things with this combination of centers. One, how to use sort of emerging technology, machine learning,
to make better manufacturing and testing. How can we feed this into manufacturing, use machine learning to understand how to improve yield, to understand how to improve reliability, etc. The other thing, we worry a lot about secure hardware. So we always worry about virus getting into software. So what he's doing is working on making the hardware. So he was invent a lot of different aspects of the hardware to ensure that you can identify, for example, is this chip really coming from a foundry in the US, or is it supposed to be from the US, but it's actually from Taiwan or something like that? But Yorgos is working on it. Go to the next one, please. We also do, and as you know, packaging is very important for microelectronics, especially for harsh environments. So we are working with Professor Wanda Gesemi. She's an expert in packaging, and she's mostly interested on high power, high voltage in particular. So that's another area that we're looking at. She's part of our center also, Chair. So she will be leading these efforts within the center. Next one, please, since I got my warning already. Like I mentioned, we have other centers that are not necessarily related to microelectronics, harsh environments, but and think about our body is very harsh. Right? So if you put an implant inside the body, if it is not stable enough, it's going to get completely corroded by your blood or fluids, and it may be quite dangerous. So we have the Texas Biomedical Device Center that actually what they do is they focus mostly on neurological injuries, but how to be able to, I won't say fix, at least treat some of these injuries using advanced electronic devices. So they sort of feed from all of these other centers that we have around, like the analog center, maybe the clean room, but they can fabricate some of these implants, lots of gadgets and extra relief. So I'll let you explain later on if you guys are interested. We have the Texas Biomedical Device Center again. And we go to the next one. What I'll show you next and last is what is our current efforts like you did that. Basically, all of these things that I showed you that we have, we started thinking about, remember that strategy to build something unique in North Texas. And we were lucky enough to convince Joe there to help us establish this North Texas Doctor Institute that has three components. Okay, so we have the Center for Harsh Environments and Microcontrollers and Systems that I will talk about a little bit in the next slides. It has a semiconductor workforce development. Remember that map at the beginning, but we have a lot of these workforce. And we're also proposing a custom semiconductor processing device. If we have, can we use some of all of these capabilities that I show you to enable this there. And Dr. Moyes is leading this, we will talk in more detail about the Texas Semiconductor Institute. But we focus on this in two aspects, chess and the custom processing device for now. So we go to the next again. So custom semiconductor processing and device support. So what do we want to do here, right? So what to do is to develop develop capabilities so that we can provide support within North Texas and the Southwest up to 100 millimeters for compound semiconductor fabrication, right? So something that is more related to what the previous speaker was talking about. So we don't have that in North Texas. We have a clean room that is well equipped. We need to get a few more tools, maybe some packaging tools, but we can use sort of UT labs. Obviously, we have the Army and the university, but we have good expertise in circuit, we have accreditation, secure hardware, we have a very strong device and circuit on device and circuit modeling, we have characterization at the clean room. How do we work and combine all of the structure that we have to be able to think? Well, we need money, right? That's what we need. And we're working with the things Texas to see if we can get some of the support that will enable this or we call it, that will be unique in North Texas. So that's working progress that we have right now. The next one
what I'm gonna show you is also the model work in progress that we have in certain commercial environments in the systems. And so what we want that is to be able to, and is there an vision to enable devices and electronics needed for harsh environment. So we have some of these facilities already in place. We started with this in January of this year. We have probe station, typical. We have a really nice here with a lot of in situ activities. We have quite a bit of radiation sources, gamma, neutron, here to acquire a new X-ray source. Last month or so. Some of the capabilities under development are down here. Okay. And what I will do next is simply show you a couple of those capabilities that we are developing as why we're doing it, why we think it would be relevant. I'll start with this two photon absorption. So why are we interested in this TPA, two photon absorption? So as you guys know, it's very important to understand this single event. Okay? To understand why are we interested in this? Because if we have a device that is operating, if we have an energetic particle or high energy photon coming through, it will create a disturbance in here, single particle, single photon, a disturbance in the device that will create this spike in the current in your device, which might quickly destroy some memory, may erase it. Sometimes it actually destroy the entire CPU. So how do we characterize it? How do we fabricate the device and go and test it for single events? So what we have to do is go to the next one here. What we have to do is we use ion beam. If we use an ion beam, we need to use a cyclotron or an accelerator, which they are very expensive, right? Millions of dollars. They're not only very expensive, obviously they are related. They are very short supply because not everybody can get $100 million to get your own cyclotron. It's very expensive. To build, they're also expensive to operate. What to do here is use a laser to be able to simulate these single events or the linear energy transfer that the ion will have in a device, but instead of using the ions in the synchrotron, we use a laser. That's why you understand how this works. So this is a very simple schematic of the TPA. I'll show you more detail in the next couple of. So this is just a comparison of a single photon and two photon absorption system. On the left hand side, so the band conduction band, single photon is what we normally expect. Photon comes in, has short wavelength, so enough energy to promote electrons from the valence band to the conduction band. So we have a single photon that will generate electron and hole pairs, so no problems there. With the two photon system, we actually send two photons with a little bit longer wavelength. So I actually need two photons to be able to promote one electron from the valence band to the conduction band, or I need two photons to generate an electron hole pair. What's the benefit of this? Why do we go to this trouble? Because in single photon, if I were to irradiate a sample, most of these electron hole pairs will be generated at the surface of the device. In the two photon, or see, we go from 590 nanometers, 100 goes a little deeper, but not deeper than 6 microns. In the case of two photon system, we can penetrate up to 20 microns, depending on the energy, up to 20 microns into the device, and I can position exactly within the volume where I want that energy to be generated, especially where I want that electron hole pair to be generated, or in other words, where I want that single event to happen in the device. So that's unique about this two photon absorption system. There are quite a bit of advantages in there, but I can say that I think in the morning I will go through. Go to the next one. This is a simplified version. Okay, so it's simplified, but it's still expensive. So put this system together is probably about $1 million or so. I want the next one. So this is just to give you an example of what can this system do. Okay. So this is basically taking an X-ray get on a specific IC test sheet to try to measure a couple of air drums air drum when different states of the end well or the free well. So the advantage of the two photon system is that you can go from the back, polish the surface, you can go from the back, you don't have to worry about absorption from the front. So go to the back and point exactly on where you want that event to happen. And without going into a lot of technical details here, so this is sort of the threshold at which a single event will happen. You can tell that by looking at this separation, which is the top separation, we can tell immediately that the wider this separation, the more likely that a single event will happen. So this is the type of data we can extract from this EPA, which is quite similar, but it will translate exactly what you will get if you were to measure this in the synchrotron. Except that the synchrotron, you will evaluate the entire device. In this case, we can be very specific in terms of where this should go. Okay. Next one. So this is the last one before my conclusion. So, and that is coming. The other thing that we put together here is the thermal imaging for active system. So the beauty of this system is that we have a very good spatial resolution. And so that's the beauty, of course. So what is the drawback of this? The drawback of this one is that we need to have a way for the light to be reflected in the surface. So we have some sort of metal in there. But we can get most of our devices we have metal, so we're not too concerned about that. But we can get, look at the size of this is 1 micron. So we can get some of the temperature profiles of a device from the operation using this tool. The resolution, temperature resolution is about 1 degree, 1 Celsius in Celsius. So we have great spatial resolution. We have very good temperature resolution. How does this work? Basically, by looking at how the reflectivity of that metal surface changes. Okay, so we have a lot of really cool optics in there. We're putting this together. Hopefully, in the next few months, before the end of the year, for sure, we will have it implemented. I think next one is just the conclusions. There you go. I'll finish under. Even though it's late. So I think that what I want to finish with is I'm really happy that as institution we have implemented this plan to organize our internal infrastructure expertise, the faculty expertise to address some of the challenges that we have in the microelectronics. I believe that North Texas is really well positioned to lead research and development in environment electronics, but we need to do some work. But I think we're well positioned. We have plenty of DoD related companies around the area. We have also regular sort of consumers of that technology as well. We have mature academic and industrial infrastructure, I think, that we can benefit from. Especially we have this driving economic ecosystem in semiconductor. I just show you the entire sort of Dallas Fort Worth area. And something that we don't talk too much about, we haven't talked too much is I believe in Roger, correct if I'm wrong, that Dallas Fort Worth is the area that has the highest density of DoD related companies in the country, right? So we have not just a semiconductor, but DoD related industry there is quite high. And later, Dr. Wright will talk about the North Texas Semiconductor Institute in more detail the next session, but the idea is that the North Texas Semiconductor Institute will be the facilitator for comprehensive workforce development. Why? Because we want industry, we want industry to be able to go to a single engine, right? So we don't want Intel to go to electric engineering, and then we have Lockheed Martin to come to material science. So the electric engineering department may say something different than material science department. So we want to send a coherent, simple, very simple message. So that's part of what this workforce development sort of effort on the North Texas Semiconductor Institute is about. Obviously, so we are also very interested in the Center for Environment, Semiconductor, Electronics, Semiconductor, and System for Electronics. And this is our next big task. So we're working very hard with our team there, you did that as a level. So what will take for us to use all of this infrastructure to be able to enable CGV compound semiconductor processing, but an emphasis in compound semiconductor, not only for electronics, but also for optics, because we do have quite a bit of laser related companies in Texas. And with that, I'll be happy to answer any question if I have time. Thank you.
We can take a question right here. Any questions? Yeah.
Curious how much like support staff you have in your clean room. Is it a lot of technicians, a couple, or?
So, yeah, it's a great question. So we have 5 bays and we have 1 technician per bay, okay? Whose only job is to keep the equipment running and train our postdoc or students. So they don't run process unless we have a request from a company to run a particular process. They go to the clean room director and the technician will run the process. But it's about, I think we have 7 technicians, but we have 5 bays, and we have a couple of technicians kind of float around with different.
So I just, so take, but then 2 process engineers as well.
Okay.
So, you know, and the benefit is that most of them probably spent 30 years at Texas Instruments before they came to us.
Sure.
So at one point, a couple of them retired. We had 285 years of experience, you know, I mean, so that makes it work.
So basically around 7 people or so, 2 process engineers, 5 technicians, plus the clean room director.
Great, cool, thank you.
On your last bullet about the facilitator for comprehensive workforce development, you mostly cater to Texas Instruments, and are you aware, but do you deal with Intel? And I want to ask you about, so in Ohio, Intel just started the OASIS program where they have universities around the area doing the same thing for them.
Yes.
Are you connected, or can you talk to that at all?
You know, I will let Ted answer that part in the next session.
Okay.
But we have a very similar effort going on in Dallas, right? I don't think that these companies like to talk to each other, right? So, for whatever reason, we know that.
I was just curious.
But no, we do have an effort going on for workforce development as well, that Ted will summarize on the next session. So I don't want to try to say something that may not be entirely accurate, so I'll let Ted. So what I can tell you is that we do have a very strong effort going on in workforce development, because that's the immediate need that we have. We don't need the compounds of the doctor, we need the center question, we need workforce ready in the next 2 or 3 years.
I can wait.
One question, I mean, I have one question for Dr. Ted and then,
Yeah, sure.
but that's later. For your clean room facility, do you partner with the local community colleges to, you know, get the technicians trained using the clean room facility that you have on site?
So in the past, we have not worked with them because there was no need for workforce. Now there is a need, and we're working. Part of what Ted will show on the workforce development is the strategy to bring, what's the 5 community college? 5 community college together to be able to be not necessarily train all the students, but be selected, maybe train the trainer or give them access to anyone in there. So again, so we did not work with them in the past because there was no need, but now through Ted's sort of leadership and the need of the Texas in the North Texas region, we're working with them to provide that research, because it's not every community college should have, and the student has a clean room. We said you can buy it, and it will be expensive.
Yeah, absolutely. Very
Right? And then, so Dallas, UT Dallas is centrally located, so we have also the community college within an hour.
Yeah.
So it's fairly straightforward. So currently, we didn't work in the past, we're working very closely. with
That's
them
good to know.
today.
Thank you.
You ready for a panel? Thank you, Dr. Schmidt.
Just want to sit on the side here.
Okay, good afternoon, everyone. As we get set up, let me thank you all for being here. I'm David Daniel. I'm the past president of UT Dallas. That's why I'm smiling and happy because it's past. I used to be Dean of Engineering at the University of Illinois and spent 16 years at the other UT. But let me thank the Wright Brothers Institute program for hosting us today. For the last set of questions, we actually had a great 2.5-hour meeting this morning between 6 or 7 Ohio University representatives, folks from UT Dallas, from Sinclair. And it was a great conversation, and I think we discovered we're all thinking about the same things and doing the same things. I know the UT Dallas folks have a list of follow-up actions to learn from what's going on in Ohio, and I think the reverse will be true as well. So our panelists kind of hijack figures, I like calling it. Call you forward. Well, let me tell you how we're going to do things. We've scheduled 50 minutes because that's what academicians know. We will take no more than that. Each of our 3 presenters will make a brief presentation, and then we'll have a little bit of a conversation. And we've saved 10 minutes or more at the end for questions from you. And for those of you who are online, I submit through the chat, I assume, and Danny or Suzanne will relay your questions. Our 3 speakers are Dr. Gio or Alex Dedon. He's assistant professor of mechanical engineering and materials engineering at the University of Cincinnati. He'll be followed by Dr. Ted Moise. He's the director of the North Texas Semiconductor Institute at the University of Texas at Dallas. And batting cleanup will be Dr. Ken Skipper. He's executive director, Aerospace and Defense Program in the School of Business at the University of Tennessee, Knoxville, and he's going to talk about supply chain. So let me ask Alex for you to come up first to give a presentation, and then we'll move on to that.
Thanks for the introduction. Good afternoon, everyone. I'm very glad to stand here and share this work with you. So you can call me Alex. I'm an assistant professor from the University of Cincinnati, connected. So I have been here in Cincinnati for a long time. I did my PhD here at the University of Cincinnati, then stayed at postdoc and 1 year and then faculty assistant professor. So my research area is mainly focusing on the smart manufacturing and maintenance. And also, for the application, mainly semiconductor manufacturing, electronics manufacturing, and also some biomedical applications. So here's a short list of my collaborators. I'm sure High-Tech and also UMC, TSMC are also my next page. So I want to begin my talk with this real alternative sponsored by NIC. So we are given funding to establish industry soldering for advanced high-mix semiconductor manufacturing. So this is the planning grant for future manufacturing you are seeing here. So according to the information I got, it needs to cut out 3 components for 3 future manufacturing you are seeing institutes. The purpose of this project is to identify top challenges and opportunities in semiconductor manufacturing, and those topics and challenges will go to the future project calls. So we have 4 institutes in our team. So you see the next page. So we begin with doing interview with big companies in semiconductor space. So this is the short list of the companies we have interviewed so far, and also for the roadmap outline presentation.
It's going by itself. I think you might have a timer on it.
Yeah, I have outline.
I'll keep them on top.
Yeah, this is the outline of our roadmap. You can see a lot of topics, but then it's related to the factory integration. So I will maybe talk about workforce development next page. Yeah, I want to share some interview notes with the company who is focused on the chamber matching. So in the shop floor, there are 500 matching chambers you need to match. But you need AI to process the data from the manufacturer.
You get a timer on it.
AI can help process data, but without human activity, the AI cannot work well. So For the five point will be, they would likely, they would prefer to spend their process engineers with to know about AI. But, this applies to the enhancement, predictive maintenance, and other activities in fact. However, the universities who train the new workforce for the industry are mainly, the student grad from university are very good at know nothing about the fab operation, no hands-on experience. So that's a challenge here, and is the activity is unlikely to change. So I'm not a person who make this comment directly cited from other places. Okay, next page. Yeah. So as for the training needs and challenges, I think I will go from group of categories. First is on-job training. It's important to get education resources like data science and other courses to the industry to give them access.
Sorry. Is that it right there? Yeah. Keep going. Okay.
Yeah. Yeah, second thing important for on-job training is private training. So I can give an example from Global Foundry. They are they are working with the community who recruit engineers to work on the maintenance. And so the engineers graduated from this program, they are graduated at the Global Foundry. For graduate level education, faculty training is also important, but the current research coming from the agencies seems to give a way of what's really needed by the industry. And also there's a technology gap between universities and the industry. So just last month's material launched their ethics center. So they welcome the youth university to demonstrate and prototype their technology using their infrastructure. I think we may become more technology center like this in the future. And also, I think the university industry collaboration is very important. So currently we only have SRC to foster those type of collaboration, but the former Senator used to do successfully in Austin, but I think they have some issues right now. And also the data IP sharing barriers need to be overcome. Either through technology or through some agreement between the institutions to foster the collaboration between university and the industry. Undergraduate level, I think we have talked about typical type people who just have, and also the engineering job are less paid than other IIs. So and also I think undergraduate level is very important to have people, have students hands-on experience operating those machines. The last point I want to mention is competition of new technology. So I think VR and AR is really important to to lower the cost of operation teams and move the training to digital. And also have talked with the primary material. They are very interested in developing a ChatGPT to become a personal tutor for their new workforce better. Yeah, next page. So here I want to quickly go through some resources that you see. We launched a new industrial system engineering program to get some training related to the data science, and we may think about semiconductor program in the future. And also Oasis, this is sponsored by Intel. So we have 15 partners in the software locale to train new workforce for the semiconductor industry. And also there are two NTxSI. You see one check the window, and one is so I'm from the sector. But trying to get back to the data umbrella. Also, I want to mention using the cost. We send students to companies to co-op. And also we have an innovation hub in 2019 foster the startup new companies and incubate new technology startups. Yeah. So last we are established industrial consortium and go for the future manufacturing US individualization in the process. Yeah.
Thank you. Come down here and then we'll, so you can see the slides and we'll all go out together. Dr. Boyce, thank you. Floor is yours.
All right, I'm Ted Moise from the University of Texas at Dallas, and I spent about 30 years in Texas Instruments, recently went to UP. And let me start off by asking you a question. Two questions. What's the population of the world? Roughly.
How much? 3 billion, 7 billion, 7 billion, okay, close enough. How many semiconductor chips were sold last year? 10 billion. 10 billion, any others? Marty?
Far more than.
Far more than 10 billion? Any others?
It's a new Moore's law, that's what you're talking about.
A trillion.
A trillion. You might have heard this quiz. So the answer is 1.2 trillion. So about 150 chips per person in the world were consumed last year. The semiconductor industry had a revenue of about $500 billion, which means the ASP, the average sale price of a chip, is about 40 cents. So chips range from little operational amplifiers that are around for 40 years and sell for less than a cent to an Intel extremely powerful microprocessor that might sell for several $1,000s. Recent up in space, it's like $20,000 or $30,000. Okay, so that's the scale of the problem that we're talking about for semiconductors and how you bring this to the US. That is, how are you enabling an industry that's able to make 1 trillion chips a year for very low cost, right? And of course, automation is a huge part of that. Next, please. So we had I'm gonna keep going. We had a meeting last year with these 4 companies in December of last year who have announced expansion plans in North Texas. And we asked them about what their workforce development needs were. Of course, TI is about $30+ billion investment global wafers here in Portland. And they said they need about 4,000 people a year from 2024 through about 2020. Of those, about 700 a year are high schoolers with some kind of certificate, ideally, or those with an AAS degree who work as operators and technicians. They also need about 2,500 bachelor's degrees this year, but the bachelors can be sorted throughout the nation, throughout the world. So in terms of actually getting people in, the locally sourced technicians and operators are harder than the bachelor's degree folks, at least right now. So we decided to try to help focus North Texas on dealing with this problem of getting operators and technicians into these bags. So next slide, please. So I'll show a version of this, and I'll mention this is Dallas over here, Fort Worth over here, Sherman, Texas up here, and the multicolored dots, which are completely undecipherable from the edge of the room, back of the room, are the different community colleges in the area. So we ended up working, just to give you a scale here, the North Texas population in this area is 13.4 million, which is ballpark the number of people in the I believe, roughly. Okay. There's about 7 million people employed, and if you look at the 5 community colleges in this region, they have a combined enrollment of about 124,000 students. These are certificates, so AS, etc. But if you look at the number of AS degrees that were conferred in 21-22, not including HVAC, in the areas of engineering and engineering technology, there's about 17 of 124,000. If you look at the AAS degrees, there's about 500. Look at certificates, about 300. So the numbers are way, way off. I looked at numbers for Sinclair Community College, close by here. The fractions are a little better, but still way off where they probably need to be. So how do we address this? What do we do about this? Next one, please. So we went to the community college. We were fortunate enough to get some support from the Department of Education. We went to the community college and we said, hey, we need to increase this output by, let's say, a factor of 3. We're going to give you some money, but we want you to increase the output. What are you going to do? And so each of the 5 community colleges said, well, for our population, we have different challenges. So for several of the community colleges, first thing they want to do is hire a recruiter because they believe the semiconductor industry is invisible to ASA. And that you need to somehow promote the idea of what advanced manufacturing is, what semiconductors are, to students who might want to participate in this. So 3 of them are hiring recruiters. One of them is coming up with whose students primarily come from a more rural area, is developing a mechatronics trailer. They're actually going to buy a trailer and send it around to the rural high schools and show students, potential students, what's going on there. A couple others are building out labs, hiring faculty, and one of them starting this or expanding their FAME program, Federation for Advanced Manufacturing Education, and we're paying full tuition and stipends to those students, and that's an earn and learn program, so those students will work for 1 or 4 companies ahead. So these are the kind of things that we're doing. Next one, please. So we came up with this tendency diagram, if you will. So we have potential students on the left, high school, veteran, reskilled, non-traditional, and we're going to be supporting recruiting, advising, and scholarships. The students are going to be going to community colleges, these 5 community colleges that I mentioned, getting certificates or associate degrees. The industrial companies are just playing mentors, and they're actually great students in here also. This whole thing is going to be evaluated and assessed in a systematic fashion by the education group at the University of Texas at Arlington. And finally, we have a path here for tuition for these students to continue their educations to the 4-year universities with tuition reimbursement. This program just started. We had a kickoff meeting a month or 2 ago. We're about to have our first quarterly meeting. We've had a follow meetings monthly. And so hopefully, this will be an interesting path to actually increase these populations. And it's, for those who've done manufacturing, this is kind of a design of experiments in terms of getting students into community colleges. What approach works best? Hopefully we'll be able to tell in 2 or 3 years, at least get an indication of what approach you want to take to recruit students and increase the output. Next one, please. This is really the summary. We have these new fabrication facilities in North Texas. North Texas is fortunately has a very large community college population, a very large high school population, about 125 or 135,000 in the area. And by putting together this consortium of community colleges, 4-year schools, industrial partners, we hope to be able to provide an ecosystem such that we can get the industry in front of the student and get them motivated for our work. Okay. All right.
Good afternoon. Thank you so much. All of you for allowing me to share a few words with you. I am Vince Skipper. I'm the Executive Director of Aerospace and Defense Program at the College of Business, University of Tennessee. We are a specific slot within the College of Business, focusing, as you can imagine, the aerospace and defense industry. Today, I'm here to just chat with you a little bit about supply chain agility, if you would. And so the secret here, I'm going to give something away. My colleagues in the supply chain world will kill me for sharing the super secret sauce, is that we are trying to actually match supply with demand. That is a game that we're trying to play. But as we all know, that is a good bit easier said than actually done. And so, if we will, oh, by the way, my presentation will be significantly lacking in Greek symbol closure. All right, so we're trying to balance supply and demand. And what many of us are, many organizations feel themselves trapped by, as they try to make their inventory match demand, and they forget about the sea of capacity in which they could make and or buy their way into additional supply. And then we're balancing all of that on the field plan, and the board, if you will, on our old teeter-totter here, is the actual supply chain itself. Now, there'll be a quiz again, but what is a supply chain? What is a supply chain? So in simple terms, right? It is everything involved in the creation of value for materials, finished good, and the return of finished good until all the use has been made up from that item. So if we recycled it or repurposed it or whatever it may be after its normal life use, right? So we're trying to balance all of that out. And as we know, in the last 2.5, maybe 3 years, especially, this has been particularly hard to do, right? Slide, please, sir. So supply chains for the last 30 or 35 years have been made for this scenario. Straightforward, go fast, right? Be as efficient and clean and lean as we possibly can be. If there is an obstacle way down the track, we see it coming. We know exactly what to do when and how to get over that obstacle in most cases, for the most part. And eventually, somewhere way down here, there's a turn, but the turn's in the same place every time. We know exactly where it's going to be, and we know how to deal with it. And for the large part, for the last 30 years, that's what we've experienced, right? even if there was a hiccup, there was a way to work around it. We could bring enough resources to bear to do so. Slide, please. Sarah. But in some cases, straight line speed is just not sufficient anymore, right? The obstacles are getting tougher. Sometimes the obstacles move, sometimes the obstacles come after us. And so we need to be able to move around them and to be able to move fast, right? So just being lean, fast, and efficient is not enough anymore, please. So in summation of all of the issues that we've seen, this is about 10 slides melted into one, so bear with me if you will. I think that if we explored each of these, we would probably find something that you have experienced in trying to sort or trying to develop supply chains for the products that you are developing. Go ahead, please slide. Let it build out. What we can say is that demands are going up. Time is getting is shrinking on us all the time, and our costs are drastically increasing across the board when we build. And our vulnerabilities and uncertainty are going up every day. Does that sound like a supply chain that you might be familiar with? So we've been doing some work in the area of supply chain agility. And we would define that as a company or an organization's ability to quickly adjust tactics and operations within its supply chain. Slide. Let it build out. And so that we've broken that down into 5 dimensions here. The top 3, alertness, accessibility, and decisiveness, are the cognitive dimensions, and then swiftness and flexibility being the more physical dimensions of supply chain agility. Go ahead, slide. So what do we do? Right. So everybody likes really simple answers. We would like one size fits all solutions that go everywhere all the time equally the same. We know that's really not the world that we live in. And so we would suggest that instead of there being one silver bullet or golden BB or platinum projectile as you like, there's no such thing. There's actually a menu of options that would help you to get to this state called supply chain agility. And so roughly broken down, and these are just a few for conversation starter, but back upstream, if we will, towards our suppliers, the reshore or nearshore. That's a topic that's near and dear to the hearts in this particular room, and one that we've heard a good deal about. But we know that doesn't happen fast, right? And even when large components are moved back closer to nearshore or reshore, many components will not. Right? That takes an extended period of time. We could also talk about how closer to the customer, right? In some cases, because we know that not all pigs are equal, sometimes we may not want a customer at all. In some markets, that's actually a viable solution to many others. It, of course, is not. And so in the middle, look at all the long list of options that we might potentially have in the middle of things that we could do to help increase our agility. Now, I won't try to go into all of these. I've already been given the 2-minute warning, and I know that we're on the clock. So I am going to speed through just a little bit and say that probably the most important piece across any of these is the willingness of an organization to collaborate with its partners to try to find problems before they're problems and generate solutions. And that's really the secret sauce. Please, next slide. So here we are back to our teeter-totter, and let it build out, please. The invisible hands out here are supplier reliability, and that's what allows us to balance that. If we know the capacity, we cannot possibly buy our way out of the inventory, so we have to depend on our partners to help increase our capacity. Good supplier capacity can balance this up a little bit, and maybe bad supplier capacity can push that down so that demand is working against us. We can also, one more, there are 2 more actually. We can move the plan. We forget that we can move the pivot point in our supply chain. So we can actually adjust our plans. Most organizations develop a plan once, they treat it as the gospel, and they never touch it again. And frankly, that's just not true. Slide. Technology can help us and help us respond faster to those imbalances. and supplier capabilities, as we said, can help or hurt our cause. The long board in the middle is what we're seeing the most action on in our episode, 2 seconds. Long supply chains become brittle and they break. So the more often we can shrink those supply chains down, it reduces our vulnerability and uncertainty to the world that happens around us, allows us to actually balance that supply chain a little bit easier. Collaboration is essential. Supply chain is impacted. Thank you.
Well, thank you, speakers, for keeping on time. That was wonderful. So I've got a long list of questions, but I'm only going to ask one of the panelists, and then I'm going to turn to you, the audience, and our online audience to ask any questions you would like. And I remind the online folks, just submit your question in a chat, and the chat question police will decipher them and decode them, and as time permits, we'll try to address them. So my question to the 3 panelists, and Alex, Ted, and Ben, we'll go in the same order, is context. I've never seen anything like this in my lifetime, where we're looking to generate thousands of manufacturing workers in a concerted nation building effort. Each of you has programs within your own institutions that, let's say, put a few students out a year or a few tens of students out a year, and we need to put out thousands of students a year. So my question is really kind of 2-part. How are you going to collaborate with others? And how are you going to take this to scale? Is it realistic to take it to scale? And give me a credible answer on your role as a university and take it to scale. So, Alex, why don't you take that one on first?
Yes, so I think a couple of since university can look to try to last for a lot of people of what is online training during the pandemic. It really changed a lot of how university works. So now I see a lot of training courses are moving to online. So last year I taught an online IMG course, which had 6 students of combination from different parts. So I think I really echo them pretty well, and they most of them have the job and so attending the online course as a part-time. And also new technology adoption. So is important. Last year I visited the Top Electron Training Center. I think their training center already overbooked. I think they are thinking to move all their training process to the cloud, to VR, and also to the digital world, so that they can get more people into the training. Same thing, and also the ChatGPT generative AI may not be a new type for manufacturing yet, but it can be a good personal tutor to train new employees and get people up to speed on the.
So Alex, I hear you saying we're trying to do something unprecedented, and we better not try to do it the same old way we've always tried to do everything. We better take advantage of new tools. Ted, how would you answer the question?
I think that's a great start. Anything that can be done online or some kind of flexible training with VR goggles or something like that should be done. For the hands-on courses, and some of it's hands-on, especially for training technicians, things like soldering, machine maintenance, or troubleshooting, whatever. For that part of it, there's really, I think, no substitute. Then build out a network of partners and have them build out a network of partners. So, for example, I mentioned these 5 community colleges that we're working with. We asked them what we do next to expand even further. Well, we did increase the number of community colleges, which is great. But the other thing we can do is ask each of those community colleges to work with N high schools that are closely affiliated with those community colleges, and have those N high schools fit out with whatever the most relevant, for example, electronic technology course certificates, things like that, and try to get the students learning those kinds of key hands-on skills in high school, so they don't have to do community college. Maybe that's at least one way to go at the scale, but it's a tough problem.
So then I asked the question in the context of workforce, but assuming they come up with a workforce and these billions of plants get built, it's gonna strain the supply chain more than ever. Is there a train wreck coming in the supply chain, assuming they get the workforce solved, and how do we avoid that?
Well, the simple answer is yes. There is a train wreck coming. We continue to do business the way we've always done. In the face of overwhelming demand, then we're going to find ourselves in the same position we are. What's that definition of insanity? And then so we have to find more ways, and it's similar to the partial solution that I talked about, I echo on the people side, is to have redundant sources of supply, multiple suppliers, additional capacity, even for if we're buying capacity that we know we don't need. And because if we wait until we need it, it likely won't be available, and then it's too late.
All right, thanks, Ben. Do we have an online question yet, Danny?
We do. So
Fire away.
So someone brought up the need for K through 12 teachers to be heavily involved in this and to increase awareness in this. Can everyone kind of speak to maybe what they think about that and maybe what their communities are doing?
Okay, who wants to take that on?
So I'll start. So K through 12, absolutely essential. In fact, even 6th, 7th, and 8th might be the place to start. And one theme that we've heard time and time again is influencing these. So how do we get the families, the community, the coaches, the guidance counselors, the teachers, to be aware of these opportunities, be able to communicate that with the potential employees, students, and there are a couple different ways of thinking of doing that. We don't have a solution yet, but that's something that needs to be spread out. And I think just anecdotally, if you ask folks who took it, who are in STEM, or engineers or researchers, if you ask them, why are you in that field? They might point back to, hey, I saw this such and such demonstration. When I was a kid, it was really fast. And I want to stick with it. So I think we need to expand that, get back to that.
Great, thanks. Okay, to our real audience, questions. Yes, ma'am, I'm here.
So, yeah, I would actually, so when you say, a long supply chain is brittle, that suggests that the shorter supply chain is more resilient. And the Air Force is actually pitching concepts, for instance, in the Smart Public Depot. This seems to be like a really good concept to introduce the K-12. Do you know efforts of doing that?
Of introducing supply chain.
Yes, things like.
So actually, yes, there are several efforts in moving forward right now. The Council of Supply Chain Management Professionals is the largest organization of supply chain professionals in the world. And there's a unified effort to actually take programming out to elementary schools. And through games, right, and fairly low tech that anybody can do. There's very little training time required to go execute that, but the message gets carried forward, right? And it's introduced to teachers, counselors, as was mentioned, and importantly, parents, right? To break down assumptions about different career fields and different industries and whatnot, so that to tell the story that there are opportunities. Did I answer your question?
No, that's great. In fact, I'd love to have one.
Well, and we'll have time afterwards. Another question from the audience, yes, sir, and then we'll go online after that.
Ben, if you were to look at education, the industry of education, and analyze the supply chain of education, what would you fix? What would you change?
Oh, wow.
And we'll wrap up after that, right? But just, big things, big problems that we have that you see from the supply chain point of view.
So from a supply chain point of view, what I would teach, and what I think we try to teach is critical thinking on how to break through problems. Instead of getting into the same old trap, same old issues, and thinking about problems the same old way that we always have. How do we teach kids younger and younger and younger to critically analyze the problem solve and be willing to stand up and take a chance, like, to fail. Right. So we've often taught kids that if they fail, they're wrong, they won't succeed, they can't go forward, etc. But what about teaching them, look, life is hard. This supply chain game that we're in is a difficult problem to solve, and you're likely not gonna get it right the first time. Think critically, dealing with it, I think probably true in your area as well, and that's what we really need, that critical thinking skills to.
All right, thanks, Ben. Danny, do you have any more online questions?
Not in a different topic, no.
I have one question.
Yes, please.
So Alex, you mentioned that we do have engineers, getting ready for semiconductor industry, but not necessarily the fab part. Actually, I have that question for you also, Dr. Ted. People coming out of UTD, how many of them really end up taking jobs in the fab? Versus design or marketing, sales, technical sales, etc.
So,
For both of you.
I don't like. So, yeah, so, I don't know the number of how many work in the fab. I will say that UTD is either depending on the year, the number 2 or number 3 supplier of engineers and science instruments. So a large number of UTD graduates are hired by TI, but they span the whole gamut. Now, with respect to engineers in the fab, right, you've got process engineers, you have equipment engineers, I do higher level equipment stuff, and you have managers. So the maybe a couple of categories, but that's primarily what we have. It's actually managers for engineers, process engineers. The vast majority of folks that, at least in my experience, are not engineers. And those folks are the ones that are needed, and those are the ones that are sourced primarily through the local colleges. And TI used to have some very big programs with community colleges on processing and other things, but those kind of faded away over the years. Now we're trying to figure out a way to bring that.
Yeah, so for this part, I think I can share some of the experience I have. So I know I've been talking to many companies, and most of them are struggling, especially in the West Coast. They are struggling to attract data scientists working fast. It's very difficult because the tech job, AI job are better paid. So I think one example from our life, we have students work, with the graduate from IT program, engineers, but they have skills of data science. So after work, they work in the engineer company for half a year, get some experience, then they jump to like Fidelity or Wall Street to do financial analysis. So I guess they are better paid.
So you're saying compensation?
Yeah.
Other questions? Yes, sir.
This might be mostly for Alex. You kind of touched on the importance of generative and I guess enabling AI technologies for technical work. Do you have any examples of good resources that can be used to help, like particularly junior engineers better understand complex technical engineering topics, aside from ChatGPT, maybe?
So you're asking using AI tools to train new engineers.
Can you identify any of those types of resources that are available now?
Yes. So we have been working with Kinetic Vision. I'm not sure if you know Kinetic Vision, close to Cincinnati, the Cincinnati local company. So they are taking up students at co-op, working at your facilities. So they provide some engineering to train the students. They have a 3D scanner, convert the object to the digital world, and then using the software to build a 3D model in virtual space. And they can use that to the students and also understand how manufacturing works, additive manufacturing, and how metrology works. I think that's a good way to train new engineers. So and also in my experience, I use ChatGPT a lot because every time I told my students, if you are unfamiliar with the new topic, you should ask ChatGPT. Then you should look paper to verify whether they are telling you that right answer or not. But this gives you some capability to quickly understand some new stuff and also improve your ability to check whether to do fact check. Basically. Yeah.
Thank you.
Danny, do we have anything else online?
No.
Okay, we're gonna take one more question, then we'll thank Bruce.
Yeah, for Dr. Skipper, one of the big advantages, it seems like the US has been, we have a pretty ample energy supply. But as we go forward with electrification for vehicles, fab use a tremendous amount data centers. I mean, are people worried about that from a supply chain standpoint? You having enough energy 10 years from now?
Area, because the greatest is so hard to address for these large demands, right? If we think about even a simple example of electric vehicles and chargers for electric vehicles, right? And so that network expands, well, the trickle charger basically is easy to do, right? We can have those anywhere, but charge it in an hour is a little different story, and that changes the demand on the network. And as we talk about much larger things, like the fabs and big data centers and whatnot, the grid doesn't change that fast, right? That's a 20-year plan to put many of those plans in place to be able to support, especially when we talk big clusters of industry. So the short answer is yes. The longer answer is it's a tough problem, and it comes down to a money issue in the end. Right? Who's going to pay for it?
Thank you.
Thank you.
All right, thank you, Ben. I have a takeaway from this whole conversation, and that is we better think creatively, really creatively and really urgently to address these problems. But audience, please join me in thanking our three panelists. Damn, you can see.
Good afternoon, everybody. All right, so I'm Gunjan Thakre. I'm representing Intel today, but I see so many familiar, names of places on all the previous presentations, because I'm originally from Dallas. I worked for TI for 17 years, up until last year, actually. And I have family.
Sorry, that's my bad.
Don't worry about it.
For some reason, it took over again.
Let me share this.
I'm just trying to get to the next presenter.
You are sharing screens.
I am.
I mean, as in.
There it goes. There it goes. I'm sorry.
Excellent. And then I graduated from UT Arlington, so that's my home market. I've seen all those names and I was like, home. So I'm a new Ohioan. And I'm glad to see that, all those familiar names. I used to live in Plano for 17 years, right? So that's that. All right, so, what am I doing here today? I am here to talk about Intel, where we create world-changing technology, but our world-changing technology improves the life of every person on the planet, right? We make sure that our technology affects, medical advances, defense advances, all kinds of things that would improve, like I said, the life of every person on the planet. We really see tech as a force of good. How do we do that? We manage it through our very published RISE goals, actually. RISE is for responsible, inclusive, sustainable, and enabling. So for responsible, we really want to make sure that our technology is helping the health and the safety of beings. We want to be inclusive. We are very, we look for diversity in thought, diversity in backgrounds. We want everybody to bring their whole self to work. We have very aggressive sustainable goals. Our goals are to be carbon neutral by 2030, water positive by 2030. These are some pretty aggressive goals, particularly if you're aware, Intel Arizona is a pretty tough place for them to have the goal of being water positive by 2030 is extremely aggressive. And yet we are going to achieve it. And enabling, like I said, bringing the whole self to work, making sure your ideas are respected and actually implemented, you feel comfortable in bringing yourself, the whole self to work. So what are we doing in Ohio? I get this question asked all the time. Are you designing? Do you have test assembly? That's for other places. In Ohio, we are focused on fabrication. We have up in New Albany, we have about 1,000 acres where we will be building 4 fabs. And so from that particular perspective, and for judging from the crowd, I don't really have to explain what fabrication is all about. So we technicians in bunny suit, I think all of us are aware of what they do. But the reason I wanted to highlight this is, we've talked about workforce development and workforce development to satisfy the needs of 4 large fabs is quite a challenge. So how is Intel influencing that? And some of us have mentioned OSS, right? Similarly, we have other programs with, so OSS is one program with like 15 institutes. Similarly, we are collaborating really with 18+ institutes with multiple, such programs. And so from what we had going on was the phase 1 of our 50 million investment commitment. The phase 1 went into, sorry, I'm still working. So the phase 1 went into, making sure that we have some competitive projects evaluated, providing them with funding. Scholarships were provided. In fact, recently we got to speak to some of the students that were, benefiting from those scholarships. And this is only phase 1. So as this phase progresses, as we see more results come out of it, some valuable projects, some interest developed within the university, phase 2 will take over. So it's more of, like we said, right? We don't know how this is going to go. We are all in a sort of a trial phase. So this is where we are as far as funding in the semiconductor education and research programs, what we call it, is. And so what are the jobs that we are looking for? This shouldn't come as a complete surprise. I do want to, because of the previous presentations that we've seen from UP Dallas particularly, where we have, people with associate's degrees, people with bachelor's degrees, of course. So we're looking for manufacturing technicians, equipment technicians, automation technicians, facilities technicians. They are generally people with associate's degrees. Now, one thing that I do want to set aside as far as Intel is concerned, we are also looking for masters. We are also looking for PhD people. So, we don't want to just limit ourselves. And this is primarily because, as you may have heard, we are the biggest proponent of Moore's Law. And so we are not really, limiting ourselves to the silicon and the silicon dioxide and the, the limitations that come from that particular material. We will explore the entire periodic table to, make sure that Moore's Law is light and well. For that, we need people with PhDs, we need people with masters, and we need people who are ready to research. So all these jobs are what essentially for new factories we will be looking for. And here's a slide where it's kind of a career pathway. The one takeaway from this slide really is that as long as you're in STEM, you have a place in Intel. So, I don't, it's an eye chart and I fully get that, but frequently, yes, we have, we have fabs and they're only looking for certain kinds of engineers, but really you can find place in Intel as long as you're in the STEM program. And so this is something that I like to end my presentations with. It hit me deeply because it says, don't be encumbered by history, go up and do something wonderful. And one of the things that really hit me personally was, I joined the industry 17 years back, like I said, 18 years back. And there were so many jobs that were inside the fab, and people basically would try to protect me from, you know, you're a woman, you don't really want to do this, you're a woman, you don't really want to do that. And it's so, it was so weird, and I was a process engineer, I should be able to do it. So anyways, the thing that has changed now, I mean, the reason it hit me was, our senior leader, Kevon, he just mentioned it, he's like, well, it doesn't matter if you cannot lift a certain weight, we have, you know, forklifts for that, we have technology for that. And that hit me, because why are we limiting ourselves with what has been done? We are in 2023. So that's why I really like to end my presentation with this. And now I'll take questions.
So you talked about the breadth of, you know, STEM backgrounds that Intel will hire in general. You also mentioned that the Ohio facility is 4 fabs. Within Intel, are those separate from something that you might be doing process development on, or do those kind of go hand in hand? Like for X number of months, we're running a 6 Sigma, you know, churning out this chipset, but for some other portion of the time, we might be doing other stuff on that line. I guess where in the Ohio facility, will you be doing any developmental process engineer work?
So it really, okay, let me answer this. If primary development for Intel happens in Oregon, it's a known fact.
Yeah.
But the way, again, coming back to this, as Intel moves towards foundry services, we have to figure out how to do things differently. Without getting into too many details of whether or not we could be doing that in Ohio, I would say that there is active interest in figuring out doing things differently than just making sure that all the development happens in one place and then the production happens.
That's right. Okay.
So there's active interest. There are no answers yet.
Yep. Okay. Thanks.
Yes.
Yeah, I'm curious about the demographics in Ohio. I mean, from what I understand, that the largest population growth that's occurred over the last several years, I think it happens in Texas, but also Florida, North Carolina, Georgia, South Carolina. So I also understand that for every job in the semiconductor industry, you need what, 7 others to be able to support. So is there a concern from Intel that basically if you need money, you rob the bank, because that's where the money is. You need people, you know, you feel like you're facing a zero-sum game in Ohio. And I understand the political importance of investing in Ohio, no question. But as you grow, how do you get around this problem? I mean, because you're going to take it from the HVAC folks, you're going to take people from different industries. The only way to do it seems to grow the population of Ohio. Or am I missing something?
Definitely way outside of my, you know, not necessarily something that I can answer for, but I will say this. You're right. I mean, we are not just, as I mentioned, our RISE goals, right? A part of it is also to attain population level diversity. So it's not, it's pretty aggressive goal. Now, I do want to say that we are targeting the Midwest. We are not just saying, hey, let's just stick to Ohio, right? It's not possible, like you mentioned. We are targeting the Midwest for sure. And we will reach all the way to Texas. Why not? They reached out to me, right? So it's not, the thing is that we need HVAC technicians as much as we need semiconductor technicians, right? So we can't just look into this one place. We have to diversify our workforce, you know, resources. We will reach out to other Texas, other states. And other Texas.
Any other questions? Okay, thank you.
Thank you.
I didn't get that out. I'm just gonna do it. That's right. About myself. So, people have been asking, how do we get people inside of us? We get into the scale. We track them when they're a teenager. That's when I fell in love with hardware. That's when I fell in love with science. That's a 19-year-old girl working in the lab. And it opened my world. I studied charge transfer effects of conducting polymers at not at high temperatures, but at ultra low temperatures, like 20 millikelvin. And it blew my mind. I was like a grad student doing work studies, and I thought I was working in the lab, so I needed money for food. And whoa, they're gonna pay you to go to Europe and to talk about it. It's just like, never telling me that that would happen in these studies too. And because I was work study, I was being paid to do this work. I realized this could be a career. That's what like, it never dawned on me that studying physics could actually be a career. I didn't see it as a joke. That's gonna be my major. And when I started like in the lab as a sophomore as a teen, I realized that what my freshman classes were only scratched the surface. It's like B is equal to IR. How far does that really get you? You know, science is a lot more exciting. It's also a lot harder. And this is why we're here. It's because it is interesting. It is fascinating. It is challenging. So today I'm going to talk about the magnetic anomaly that students can do to create maps of safe evaluation, to get them excited about stuff like that. Next slide. We're going to talk about what is magnetic anomaly map and why does it need it? You might not be familiar with this. I wasn't a couple of years ago. And how are these maps made? I'm targeting, teenagers. In fact, what group I wanted to, like 8th grade through 10th grade. And the students gain real experience. Their measurements will be used by scientists for safer navigation. So they see like, hey, this is practical. This is like, this has a purpose. What I'm doing has meaning and has purpose. Next slide. Something else here. Next slide. Well, magnetic anomaly maps. So 1/4 of the distributed critical gap capability gap. If you can think, without GPS, how are you going to get there? You're not. It's like you need some alternatives to GPS. And this is a huge problem. Next slide. So they're in the high seas. Next slide. So there are oceans that contain, lots of, high value trojans like, plasma screen TV. And pirates know this. Pirates aren't stupid. They have been known to spook GPS to different partnerships. And so this is a real problem. People are worried about transportation, like talk about supply chain. Well, if a pirate hijacked your ship and you lost your cargo, you have a supply chain issue. Next slide. And they trust GPS implicitly. And how many people use GPS to get here? And GPS goes to go left, you live left. And then GPS goes 10 more miles, you 2 more miles, even if it's 2 off there. And this happens. And if the GPS is spoofed, and it's not telling you to go 2 more miles, you're in trouble. So next slide. There needs to be a way for you to, like, hey, is my GPS signal good? It's like, is it, validate that GPS signal? And can it, can I use this for navigation? But then, well, if my GPS is bad, how do I get to point A to point B? And this is where magnetic anomaly maps are useful. Next slide. But first, we gotta take a step back in earth science. See, in high school, you probably learned that the earth has a magnetic field and people used to travel like with a compass and that's how Columbus got here. Well, there is a lot. That's just scratching the surface of a magnetic field. So yes, we have a magnetic field. This magnetic field protects our atmosphere. It saves our circuits from a whole bunch of electromagnetic radiation that's done. And so these are magnetic field lines, Earth's magnetic field lines, and how it's interacting and affecting the sun. So yeah, this is a lot more complicated than when you first thought about it in high school. Like you talked like the Earth has a little bar magnet, points north, points south, and that's about it. Next slide. And you can see that there are variations in this Earth magnetic field. So this is an intensity, like this is more north, this is south. But here in the South Pole, there's some weirdness going on. So it's just more scratching the surface, I think, are magnet. And the Earth magnetic field is pretty large because it protects our glass from the solar flares, about 20 to 50,000 nanotesla. It's a lot smaller than an MRI. An MRI is like a billion nanotesla. It's huge. It's like one Tesla. Next slide. But magnetic anomaly is different. This is the variations of the Earth's magnetic field locked in the crust. And these variations don't change that frequently. They change on order like of 20,000 years. So that's nice because if you make a map, it's going to be good for a long time. And it's like, and so they do change, but you can correct for them later. Next slide. However, they're really, really small. So the Earth magnetic field, 20 to 50,000 nanotesla, magnetic anomaly, you're looking at small signals that vary like 500 nanoteslas. So you're looking at small signals on top of a really large signals. And that's how you build these magnetic, and this here right here is the magnetic anomaly map of the US. Next slide. So I have a magnetic anomaly map. No. Slide. You need higher resolution for navigation. Next slide. How do you get to the grocery store with this resolution on the map? You can't. That's help you get here. You need that higher resolution so you can do that last mile, last 10 miles. Well, not Columbus trying to like need to go west. You know, we need to have higher fidelity because this legitimate concerns. If you're flying from Japan to South Korea, there's some places that your plane better not fly over if you want to make it to South Korea. So you need these high resolution maps. Next slide. So how are these maps currently made? It's really expensive. Like currently they have like, especially for planes with a boom that hangs out the back that's far away from the plane itself, and they fly over an area. And then this is me at the bottom with a magnetic sensor doing some work for Apple. Actually calibrate a C-17. So if you don't have that magnetic boom hanging on, you make these maps that say C-17s fly everywhere all the time. You put a magnetic sensor, you need to somehow cancel out. But it's really expensive and there's a lot of post-processing you have to do because you can imagine the plane itself is a bar magnet. It has engines that's spewing electromagnetic radiation and all these other components. And you trying to use airplanes, it's a hard route and it's a lot of post-processing you have to do. So the solution is, next slide. Next slide. Weather balloons. Weather balloons though are nice. Well, they're cheap. They go where they go. They don't have any magnetic fields that you have to subtract out. Next slide. And you go navigate the Earth's time. So you launch that plane, you get a lot of points, a lot of data over and over again as it flies through. Next slide. Back to STEM. So as you can see that, but how like the STEM, next slide. Well, it's see the value of STEM. That's why we don't go into it. It's like, and you do a simple like exercise. It's not relevant to anyone. It's like, put how many pennies on a boat and I write down the end. And it's just like, what the heck? Why am I doing this? To do research. Say, hey, this salt, this means you fly an airplane, you're going to be safer because you did these measurements. This is personal, this is real. They are contributing to science. And that is like, that I'm hoping will give them more exciting too. And it's not isolated knowledge, it's background, earth science. Before you even talk about the electronics that's going into, did you just learn? And it's like, whoa, earth science is a lot more interesting. There's a lot more going on. You start pulling these different fields together and you see how science is more of a community. It's more broader than what you thought. It's not this isolated thing. It's not just B is equal to IR. Boom, you're done. Well, there's a lot more to electronics than that. Next slide. So, both earth science, physical science, and electromagnetic, they have to build that circuit. They are building a circuit. They are like interfacing with it. They're pulling data from it and pushing it up to the cloud. This, it starts to see how all these things get together. I want to have them like each step they build through like milestone rewards, because it is so important to understand that this is a field in which you can have a career. And how do you realize that? It's simple. You give them something, money, like t-shirts, and then you're like, hey, this can be a career for me. I get something from it, something tangible, versus just like, hey, go next slide. So now, for these different milestones, they start to they register for a program, they create a blog site, and they learn about magnetism and earth science. And then they build that sensor, they start learning about electricity and power. It's like, well, if you need to, the sun goes down for 12 hours and you still need to collect data, how much power are you going to need? And it's like, these equations actually mean something. It relates to something physical and tangible. And ideal gas law. How many people oh, about ideal gas law? I'm like, why is that factor? Well, if you're launching a balloon, you gotta have a different pressure and temperature when you add it to the atmosphere. So you have to understand, if I fill that balloon up all the way at the ground, and as it launches, it's going to expand and explode, and it's not going to go anywhere. So it's like Pat's laws and words and I could get that little key things, and I start saying that, hey, these are important things, and this is what I need to understand to actually build something tangible and concrete. Next slide. And so this, how big about, I'm trying to build these kids out for next year. I'm still just slowly building this out. This is what I do on the weekends. This is not my day job. So I'm looking for funding so that I can actually start progressing on this further. So if you have any ideas where I can get funding so I can start building prototypes and getting this in the hands of teachers, I would love to hear more. And that's it.
Questions? Thank you. That's it. I think everybody's welcome to come to DEC if you like, just across the parking lot, straight across. All right.
I just want to say thank you to you on behalf of UT Dallas to WBI for welcoming us. And Jim and Eric have been playing this so incredibly easy for us, and we really look forward to sharing what we're doing nationally and partnering with everyone here. So.
Thank you.
Oh, we can.
It just doesn't need that challenge. Yeah. Yeah.
Yeah, I would.
Let me tell you.
That's. You know.